Okay, we will start in 1 minute. I will present to Professor Pfefferman, and then Professor Pfefferman will be able to start. Okay, so it's my great pleasure to present today the first speaker of the ICMAM Satellite Conference in Analysis and PDE. So today we have as the first speaker one of the most influential mathematicians in the area of analysis and partial differential equations in the last 50 years, Charles Pfefferman. Professor Pfefferman is professor at Princeton University. He was awarded the Fields Medal in 1978, as well as other prestigious awards during his career. His contributions vary over a wide range of topics in analysis, and today he is going to speak about equations for unknown CM functions. So thank you very much, Professor Pfefferman, for accepting our invitation, and please go ahead.
Okay, so thank you for the invitation. I'm very happy to take part in this conference. Before we get started, I just want to make sure, can everybody see the PDF that says equations for unknown CM functions?
Yes.
Yes, okay, great. And as it says on the slide, that's joint work with Garving Lully. Okay, we've got trouble. I was able in the rehearsal. There we go. Wait a minute. I wonder why is it that I'm unable? I'm sometimes able to move the slides. This should be interesting. I want to dedicate this lecture to the memory of Alberto Calderon. Whoa! Wow! I'm unable to move the slides. Okay. There is a fallback position. Give me a moment to switch to a different mode of presentation. Never a dull moment. Let me stop sharing. Stop share. Okay. Here, share screen. Advanced sharing options. Whoop. That's wrong. All right. Give me a moment. Aha. Okay. Advanced. Content from second camera. There, now let's see. Aha, except that it's upside down. I'm not sure what to do. Oh, I know what to do about that.
Wow, we can see your slides
Yes.
in paper. Very nice. Thank you.
Sure, okay. There, isn't this exciting? Okay, so, okay, yes. Well, apologies for the mode of presentation. What can go wrong will go wrong. All right. Again, I'd like to dedicate this this lecture to the memory of Alberto Calderon, with whom I was privileged to work during my days as a young mathematician. Okay, this talk is about linear equations for unknown CM functions. Okay, so here, if I can move the slide, there is an equation for unknown CM functions. So the A's and the little f, the lowercase f, are given functions on Rn, and the capital F's are the unknowns. And we want to solve this. So these are functions on Rn, and we want the unknown functions to be CM functions on Rn. Okay. In particular, we want the unknown functions to belong to CM of Rn for a fixed m. We're not allowed to lose derivatives. If we want functions with 10 derivatives, it's not enough to produce functions with 8 derivatives. So m is specified. Okay. This subject started with the C0 case, merely continuous rather than CM, and it was introduced by algebraic geometers, Brenner, Epstein, Hochster, and Kolar. I'll say a little more about why they were interested in it. Okay, so the motivation was different for Kolar as opposed to the others. So Janos Kolar asked simply, how can we tell when a rational function is continuous? So the trouble is that the numerator and denominator may have common zeros. And so the ratio is only defined outside some algebraic variety. And one has to know whether that function can be extended continuously to the place where P and Q are both 0. Okay, and so that natural question means simply that the linear equation Q times F equals P has a continuous solution, capital F. So in the C0 case, when there's one unknown function, we're interested in knowing whether a given rational function is continuous. The other algebraic geometers, Brenner, Epstein, and Hochster, were interested in notions of the closure of an ideal in a polynomial ring. So given polynomials A1 through AD on Rn, if you look at the polynomials little f, for which the equation admits a continuous solution, then those little f's obviously form an ideal in the ring of polynomials. And so obviously the A1 through AD themselves belong to that ideal, and that ideal can be thought of as somehow a closure of the ring generated by A1 through AD in the polynomial ring. And because algebraic geometers were interested in notions of closure of ideals, they asked this question. Here's an example that they looked at. Suppose we were on R3 with coordinates x, y, and z. I give you a polynomial little f, and the question is whether there exist continuous functions, capital F, 1, 2, and 3, that solve the equation that you see on the slide. And we'll come back to that example later. Okay. Now, all right, let me pose 3 questions. So far, I haven't actually said what the questions are. I've only said a little bit about what the subject is about. Now I'm going to pose 3 specific questions. So the first question is this. We fix little m, the number of derivatives, little n, the dimension of the Rn we live in, and capital D, the number of unknown functions. Now, given functions A1 through AD and little f, functions on Rn, maybe they're polynomials, maybe they aren't. The first question is, how can you decide whether there exists a CM solution to the equation? And so that's the question in the box. Okay, that's the first question. Second question, which goes more to the Epstein, Hochster, Brenner point of view. We fix our M, N, and D, and we definitely assume now that A1 through AD are polynomials. And we look at polynomials little f, for which the equation, the linear equation, admits a CM solution. Those little f, again, obviously form an ideal in the ring of polynomials on Rn. And the problem is to compute generators for that ideal. How can we calculate them? And the final question is, Here, wait a minute. The final question is, suppose that we're given the A's and the little f, and suppose that they're polynomials, and suppose that our equation does have a CM solution. Well, what kind of CM solution do we have? What kind of functions are these capital Fs? Can we take them to be rational functions, for example? Turns out the answer is no. Can we take them to be semi-algebraic functions? Turns out the answer is maybe. We'll see. So I would just like to review, to remind you what a semi-algebraic function is. So first of all, a semi-algebraic set in Rn is a union of finitely many sets, each of which is defined by a finite number of polynomials, and some of these polynomials are required to be positive, and other polynomials are supposed to be zero, and so E is a union of finitely many such sets. So it means that given a point of Rn, if you want to decide whether that point belongs to E, you can just evaluate finitely many polynomials at that point and see which answers are positive and which answers are negative and which answers are zero, and that will tell you whether the point belongs to E or not. That's a semi-algebraic set. A semi-algebraic function is a function whose graph is a semi-algebraic set, as shown on the slide. So the graph is simply, well, it's shown on the slide. Okay, so that's a semi-algebraic function. Okay, now it turns out that we can answer the first two questions, but we have only partial results on the third question. All right, now before I say anything about the answers to these questions, maybe I should explain how I came to get involved in questions that came originally from algebraic geometry. I'm, of course, not an algebraic geometer. So what happened was, yes, and an email from János Kollár. One day I was minding my own business when Kollár, a very distinguished algebraic geometer, sent me a description of problem 1 and asked, do I know anything about that problem in particular? And I immediately replied, no, I know nothing about it at all. However, I started thinking about it, and I realized to my great surprise that in fact the answer is yes, I know a lot about it, because, well, I'll explain why it turns out I knew a lot about it. But first, the result of my knowing a lot about it was a joint paper, a very strange joint paper written by Kollár and me, giving two completely unrelated solutions to question 1 in the case of continuous functions, so m equals 0. Okay. So Kollár's solution involves some algebraic geometry that I wish I understood, and my solution involves some very elementary analysis. Maybe conceivably, Kollár would say it's analysis that he wishes he understood, but it's very elementary. I bet he understands it. Anyway, all right. So why did it turn out that I knew something about this problem? And the answer is that these 3 questions are very closely related to a problem that I've spent years thinking about. And that problem is Whitney's extension problem, which I would like to pose next. Okay. So here is Whitney's problem, which he posed in 1934. Let's fix little m and little n, and suppose I give you a function phi mapping E to the reals, where E is a compact subset of Rn, but I make no assumptions about E other than that it is compact, and so it could be just awful. Okay, and the question is whether this function phi extends to a CM function on Rn. That is, as it says in the box, decide whether there is a CM function on Rn that agrees with phi on E. That's Whitney's extension problem. Okay, now it turns out that the 2 questions, on the one hand, Whitney's extension problem, and on the other hand, the first of our algebraic geometry questions, these 2 questions are both special cases of a basic question about bundles. Bundles don't, in this talk, bundles don't mean what you think they mean. I will shamelessly steal the word. but it doesn't mean what it normally means in geometry and topology. Okay. So the plan of the rest of the talk is that I'm going to define bundles, fibers, subbundles, and sections of bundles. Once I define those concepts, I will pose the main question about bundles and explain its solution in terms of something called Glaser refinement. I'll define that also. Okay, and it turns out that that will solve question 1. And if time permits, I'll discuss the solution of problem 2, and I will say at most a few words about problem 3. Let me interrupt and just ask, when should I finish?
At 250 to 55.
Okay. Okay. All right. So let's prepare to define bundles. I need some notation. So we always fix our little m, the number of derivatives we want, our little n, the dimension of the Euclidean space Rn on which our functions are defined, and capital D, the number of unknown functions. All right. Script P is the vector space of polynomials of degree at most m on Rn. And we think of a polynomial in script P as the Taylor polynomial of some function at some point. So Jx of f is my notation for the nth degree Taylor polynomial of f at x. J being, why do I call it J? Because I say that this is the jet of f at x, okay? So the jet at x of f is a polynomial in script P. Okay, so we're going to be taking Taylor polynomials of functions. Okay. I'm also going to be taking jets or Taylor polynomials of vector valued functions. And so there's the obvious notation. Cm of Rn Rd denotes the space of Rd valued Cm functions as on the slide. And for each such creature, we define its mjet just component-wise, again, as on the slide. Okay. So now we can take Taylor polynomials of vector valued functions. Okay, now there's a natural multiplication in script P called jet multiplication. If we're given two polynomials P and Q in script P, their jet product at X, denoted as on the slide, is defined by first multiplying P and Q in the usual way as polynomials, but then taking the Taylor polynomial of that at the point X. And so the point of that definition is that the jet of Fg for two smooth functions F and G, the jet of Fg is equal to that product of the jet of F with the jet of G. And that makes the set of all possible jets into a ring, which I call R sub X, the ring of M jets at X. Now, of course, as X varies, these rings are all isomorphic to one another, but they're not identical, and it's convenient to keep them separate for the moment. Okay, so that's Rx. So this is all just notation. Okay, well, all right, more notation. So Rx to the D just denotes the direct sum of D copies of this ring Rx. And so elements P1 through PD in Rx to the D can be multiplied by a jet Q, and the multiplication is just component-wise, and that makes Rx to the D into an Rx module. Okay, this reminds me that maybe 50 or 60 years ago, I passed an exam in which I had to know a little bit of algebra. Okay. All right. So we're going to be looking at Rx submodules of Rx to the D. And we'll see examples in a few minutes. And we'll see that in fact, our questions, both Whitney's extension problem and our algebraic geometry questions are really questions about Rx submodules of Rx to the D. I want to spend a moment just talking about exactly what I mean by a submodule. The following degenerate cases are going to be allowed. So if I look at the full module, I consider that as a submodule of itself. Okay, so Rx to the D is allowed. The zero submodule is allowed. and a very strange, maybe unconventional choice, the empty set is going to be allowed as a submodule of Rx to the D, and we'll see that it's actually important to do that. So that's a little strange, but bear with me. Okay, so that's what I mean by an Rx submodule. Okay, and now armed with that notation, we can define bundles, fibers, subbundles, and sections. Okay, so suppose that E is a compact set in Rn. A bundle, let's see, how can I, there. A bundle is defined to be a family, as shown on the slide. It's denoted script H, and it's a family of objects called H sub X, where X varies over the points of E. And for each point X in E, HX is a translate, or if you like, a coset of an Rx submodule of Rd. So HX is equal to Fx, which is an element of Rd, plus I sub X, which is a submodule of Rx to the D. So this is by now looking probably very strange and unmotivated, but we'll see examples in a moment. And in fact, we'll see that, again, that Whitney's extension problem and the algebraic geometry questions make sense in this strange context. It's important to do this rather than looking at those questions in their own right, and we'll see why. Okay. Note that any particular HX might be empty because we allowed the empty set as an Rx submodule. So we have a family of translates of submodules parameterized by the points of a compact set E, and some of those translates of ideals might in fact be the empty set. Okay, so we now know what a bundle is. Well, the base of a bundle is simply that compact set E. And if X is a point of E, then HX is the fiber of the bundle at the point X. And so if you compare that with the usual definition from geometry and topology, that's not so totally different. Okay, if you have two bundles over the same base E, then one is a subbundle of the other if the fibers of one are subsets of the fibers of the other. Not necessarily proper subsets. So for example, every bundle is a subbundle of itself. And so I'm going to write that H contains H tilde if each fiber of H contains the corresponding fiber of H tilde, and then H tilde is a subbundle. So these slides are zipping by quickly, but I hope that each individual slide is quite easy to understand. Let me just ask, is anything unclear? Please, anybody should feel free to ask questions.
Okay, so at this point, someone has some question. Are there any questions for Professor Pfefferman? You can raise your hand. Okay, it seems that people is happy.
Okay, fine. Okay, if people are happy, I'm happy. So we continue. All right, so these are bundles. All right, so now let's see, what is a section of a bundle? Well, suppose that H is our bundle, and suppose that F is a CM function taking values in Rd. What it means for F to be a section of this bundle is that at each point of the set E, the jet of F, that is the Taylor polynomial of F, should belong to the fiber HX, the fiber of the bundle. Okay, that's what it means for F to be a section of a bundle. Okay. And now I can at least state the main question about bundles, which is, given a bundle, decide whether it has a section. That's the question. Now, all right, let me make immediately a trivial remark. If our bundle has even one empty fiber, obviously it has no sections. The jet at a given point X is not allowed to belong to the empty set. Thank you. Okay, so that trivial remark will be important. Okay, now I'd like to show you, after all this strange looking notation and these definitions, I'd like to show you that the Whitney extension problem and the first of the Brenner-Epstein-Hochster-Kolar problems are in fact both special cases of the main question about bundles. So let's start with the Whitney problem. So suppose I'm given a function phi on our compact set E, is there a CM function that agrees with phi on E? Well, for each point X in E, let me define HX as on the slide. It's simply the set of all polynomials P in script P, which take the value phi at X. So P agrees with phi at one single point X. Then you can check just trivially from the definitions that the collection of all of those HX is a bundle, and a section of that bundle is precisely a CM function capital F that agrees with phi on E. And therefore, it follows at once, that there exists the desired F if and only if that particular bundle has a section. So if we can answer the main question about bundles, given, here's a bundle, does it have a section? That means that we can answer Whitney's extension problem. Now let's look at the Brenner-Epstein, Hofstadter-Kolar. Maybe I'll just abbreviate that by saying algebraic geometry. The first algebraic geometry question. So are there CM functions satisfying the linear equation shown on the slide? Well, for each point X in Rn, let Hx be the set of d tuples of polynomials that satisfy the equation in question at the single point X. The collection of all of those Hx, as X varies over Rn, is a bundle. And a section of that bundle is precisely an RD valued function that satisfies the linear equations. And therefore, there exists a, there exists a CM solution of our linear equation if and only if this bundle has a section. Now, I've cheated a little bit because bundles are supposed to be defined over a compact base. And the last bundle that I wrote down has Rn as a base. That's not compact. So technically what I said was a bundle is not actually a bundle. But that's a trivial technical point. I don't want to waste time by explaining how to overcome it. Trust me. Okay. So if we can, so the upshot is that we have defined bundles and we've posed the main problem about bundles. And we've seen that both Whitney's extension problem and the Brenner-Epstein-Hofstadter-Kolar problem Q1 are special cases of that main problem about bundles. So now our next order of business is to say something about how we solve the main problem about bundles. And it turns out that, well, let's see what's the next part. Yes, next we sketch the solution. The solution has the property, maybe I will say this here. Before I say anything about math, let me give proper credit. First of all, my co-author and friend is Garvin Kevin Luley, and we didn't work in isolation. We built on decades of previous work, going back to Whitney in the 1930s, Georges Glaser, my French pronunciation is no good, I will just say Glaser, Georges Glaser in the 1950s, Yuri Brudny and Pavel Schwarzman from the late 1970s through the 2000s, and then Ed Bierstone, Pierre Millman, and Vyacheslav Podlutsky in the early 2000s. So I'm not going to mention their work except to say that it was important and we built on it. Okay. All right. So remember our main question, how can we decide whether a given bundle has a section? And to answer the main question, we're going to introduce a concept called the Glaser refinement. Okay. The definition is a little bit complicated, and so I propose to approach it carefully and stealthily. So given a bundle, we're going to define its Glaser refinement. The Glaser refinement of the bundle H is the bundle H tilde as shown on the slide. Notice that H tilde is again a bundle over the same base as H. Okay, so I haven't yet defined it. And in fact, I'm not going to define it for a little while. Instead, I'm going to tell you what it does. And then later in the talk, I will tell you what it is, and we will check these properties. So the key properties of the Glaser refinement are the following. The Glaser refinement of a given bundle is a sub-bundle of the bundle that is being refined. So the fibers of H tilde are in principle smaller than the fibers of H. Nevertheless, H and H tilde have exactly the same sections. And furthermore, H tilde can be computed from H by doing linear algebra in fixed dimension and then taking a limit. Those are the three key properties of the Glaser refinement. So I ask you to take those properties for granted, and we will use them to solve the main problem about bundles, and then we will come back and define the Glaser refinement. All right. So if we want to know whether our bundle H has a section, we may as well ask whether H tilde has a section, because H and H tilde have the same sections. So what's happening is that we pass from H to H tilde by discarding junk. Junk being elements of a given fiber that can never possibly arise as the jet of any section. Okay. Now, even though all of the fibers of the bundle H are non-empty, it may happen that when we Glaser refine, the H tilde, the Glaser refinement, has some empty fibers. In that case, obviously, H tilde has no sections, and consequently, H has no sections because H and H tilde have the same sections. Okay, so we can use the Glaser refinement to test for obvious obstructions to the existence of a section. We can carry that idea further by performing iterated Glaser refinement. So given a bundle H, call it H0, and then we Glaser refine H0 to produce the bundle H1. And then we Glaser refine the bundle H1 to produce the bundle H2, and so on. And so inductively, we have bundles H0, H1, H2, and so on. And there's the induction. H0 is our given bundle H, and HL plus 1 is the Glaser refinement of HL. Okay, now notice that we can compute HL because we can compute the Glaser refinement of a given bundle from the given bundle. And so we just iterate that, that computation. And so each HL is an object that we can compute. Furthermore, for each HL, the sections of HL are exactly the same as the sections of H, and that's an obvious induction from the property of the single Glaser refinement. It turns out that the process stabilizes. So there is this integer constant L star determined by our little n, and D. And if you Glaser refine L star times, then you have discarded all the junk you can possibly discard, and further Glaser refinements just produce the same bundle over and over and over again, as shown on the slide. Okay, so it makes sense to Glaser refine L star times, but it's of no use to Glaser refine more times than that. Okay, now that allows me to answer the main question about bundles. So given a bundle H, we Glaser refine it L star times, and then we look at this bundle H sub L star, and we ask whether it has empty fibers. If it has any empty fibers, if it has even one empty fiber, then H can have no sections. But that's the only obstruction, and the theorem is that H has a section if and only if H L star has no empty fibers. Okay, that's the answer to the main question about bundles. And so we have answered both the algebraic geometry question Q1 and the Whitney extension problem. Notice that we had to talk about bundles in general rather than just talking about the Whitney problem or the algebraic geometry problem, because even if the bundle H to start with comes from something that we recognize, nevertheless, by the time we have Glaser refined it L star times, God only knows what it is, and we had better be in the general context of bundles. That's why I posed this general framework. Okay. All right, so we've answered the main question about bundles, except that we haven't defined the Glaser refinement. And so in the next few slides, I'm going to do that. Oh, let me move the cursor. It seems to be in the way. Okay. So as motivation for the definition, I want to mention a simple property of CM functions and their Taylor polynomials. This is simply Taylor's theorem dressed up in fancy clothes. So if you have 2 points of Rn and you have a CM function, if those 2 points are extremely close together, then their Taylor polynomials are also close together. And here is the quantitative statement. Fix a point x0 in Rn. Given epsilon, there exists a delta, so that for any 2 points x and y that lie in the ball of radius delta about x0, we have the estimate on the slide. Okay, so the jet at x and the jet at y of our function f are so close that the estimate on the slide holds, and that's just Taylor's theorem. There is an embarrassing degenerate case if x is equal to y and the order of our multi-index alpha is equal to m, the right-hand side is 0 to the power 0. And so in that case, we just make the convention that 0 to the power 0 is going to be defined to be 0. Okay, so that's Taylor's theorem, and we'll see that estimate again in the definition of the Glaser refinement. Okay, so now let me fix the sufficiently large integer constant k determined by our little m, little n, and d. And now finally, I can give the definition of the Glaser refinement. So let script h be a bundle. The fibers of script h are h sub x, as shown on the slide. The Glaser refinement is then h tilde, a bundle over the same base E with fibers h tilde x. And what I have to do is tell you what h tilde x is for each particular x. So let's fix an x0 in E, and I'm going to give you on the next 1 or 2 slides, I'm going to give you the definition of h tilde x0. So come on. H tilde x0 consists of all the polynomials p0 in the fiber of the original bundle at x0 with this special property. Given epsilon, there exists a delta so that if you pick any k points in the ball about x0 with radius delta intersect E, k, remember, is that integer constant, then there exist polynomials p1 through pk, each p belonging to the fiber of the original bundle at the appropriate point, as shown on the slide, and satisfying the estimate that you see in the box, which looks familiar from Taylor's theorem, where notice that the indices I and j vary from 0 through k. An important peculiarity of this slide is that although p0 through pk appear sort of on the same footing in the estimate at the toward the bottom of the box, nevertheless, p0 and the other p's play a very different role in this definition. x0 is a given point. p0 is a given jet. It belongs to the fiber at x0, and we are testing whether it belongs to the fiber of the Glaser refinement. So x0 and p0 are fixed. And now for every epsilon and delta, and for every x1 through xk, there are supposed to exist p1 through pk that do something. And so that means that while the p0 is fixed, the p1 through pk will vary with x1 through xk. Okay, so that's the content of this next slide. Even though they all appear in the definition, p0 stays fixed while the other p's vary. So that's the definition of the Glaser refinement. And now that I've finally given the definition, I would like to check the key properties that I asserted originally. Remember what they are. The first key property is that h tilde is a subbundle of h. That's obvious from what I've said, even though the definition of the Glaser refinement is a little complicated, because we're given our bundle h, and we defined our bundle h tilde by saying that h tilde x0 consists of all the p0 in hx0 such that blah, blah, blah for some complicated looking blah, blah, blah. Well, if that's true, then of course h tilde x0 is contained in hx, in hx0, excuse me, as shown on the slide. And that means that h tilde is indeed a subbundle of h. That's all there is to it. So key property 1 is completely obvious. Not quite so obvious is key property 2, which is that h and h tilde have the same sections. Now, h tilde is a subbundle of h. So the fibers of h tilde are subsets of the fibers of h. And so every section of h tilde is obviously a section of h. What we've got to show, which isn't quite that obvious, is that every section of h is also a section of h tilde. That's the content of key property number 2 of the Glaser refinement. Okay, and so here's the idea. Well, suppose that f is a section of h. Our job is to prove that it's a section of h tilde. All right, what does it mean that f is a section of h? And what do we have to show to prove that it's a section of h tilde? Well, f is a section of h, so it's a CM function. And at each point x, its jet belongs to the fiber hx. That's what it means for f to be a section of h. What does it mean for f to be also a section of h tilde? Well, it means that for each point x naught in E, j sub x naught of f belongs to the fiber of the Glaser refinement. What is the fiber of the Glaser refinement? Well, it means that the stuff in the condition in the box holds. Given epsilon, there exists a delta such that for any k points of E that lie in that ball of radius delta about x0, we can find polynomials p1 through pk in the correct fibers of our original bundle H that satisfy the estimate shown on the slide, where I and j vary from 0 through k, where here p0 is the jet of f at x0. That's what we've got to show. Okay. Is it clear? I'm afraid it's maybe the least clear of all the slides in the talk. Okay, I hear no objections. So that's what we've got to show. And the way we do it is that we simply set P1 through PK equal to the jet of our function f at the points x1 through xk, as shown on the slide. If we do that, then of course P1 belongs to hx1 and so on, PK belongs to hxk. We know that because f is a section of h. And how about the inequality in the second box on this slide, the inequality with the epsilon in it? And that inequality is because each p is the jet of f at the point xi or xj. This inequality is just Taylor's theorem for the CM function capital F, as I mentioned a few slides ago. And so that's it. That proves key property 2. Every section of H is also a section of the Glaser refinement of H. So it comes down just to Taylor's theorem. Okay, so we've proven key property 2. All right, now key property 3, H tilde can be computed from H. So let's see what kind of computation we're doing. So we're given our H. Now, given points x0, x1 through xk in our set E, and given polynomials p0 through pk belonging to, each belonging to script p, so each a degree at most little m, we define a quadratic form as on the slide. Those things that look like vertical bars or maybe like parentheses, those are vertical bars because maybe the p's are vector valued. So this is a Euclidean norm squared. Okay. So let me take a moment to let you just look at the definition of Q. Okay. So now, okay, notice that this Q is a quadratic form in the P's once I fix the X's. I'm going to define script Q of P0 and a bunch of X's as the minimum of Q where P1 varies over HX1, P2 varies over HX2, and so on, PK varies over HXK. Well, then this script Q is the minimum of a quadratic form over an affine space, and so we can compute it by elementary linear algebra. Okay, now if you chase the definition, you will see that a given P0 in the fiber at X0 of the original bundle H belongs to the fiber of the Glaser refinement if and only if that quantity script Q tends to 0 as X1 through XK in the obvious Cartesian product of E tends to the point X0, X0, dot, dot, X0. Okay, and so we can decide whether that's true by doing linear algebra in fixed dimension to compute script Q and then taking the limit as in the box. So sure enough, we can compute H tilde from H by doing linear algebra in fixed dimension and passing to a limit. And so we have defined the Glaser refinement, checked its 3 key properties, and used it to state the answer to the main question about bundles, namely how to decide whether a given bundle has a section. Okay, now there's something that I've left out. I've left out the hard part. Namely, we haven't discussed at all the proof that the answer that I gave to the main question about bundles is correct. That proof is long and hard. And so I propose to say absolutely nothing about the proof. Let's just believe it. Okay, and so now we have answered in particular the algebraic geometry question number 1 by reducing it to a question about bundles, which we then answered. Let me now move on to the second of the algebraic geometry questions, namely, given finitely many polynomials A1 through AD on Rn, look at the polynomials expressible in the form A1 F1 plus and so on AD FD, where the capital F's are CM functions. So look at all such polynomials. Those polynomials form an ideal in the ring of all polynomials on Rn, and the problem is to compute generators for that ideal. That's the second question, and we're going to answer that question in the next few minutes, or at least talk about it. Again, the results are joint work with Kevin Luling. Okay, now I want to start with a little observation. This question cannot be solved by analysis alone because it's about finding generators for an ideal in a polynomial ring. That's not an analysis topic, that's an algebra topic. On the other hand, we can't solve this problem by algebra alone because it has to do with CM functions, and that's not an algebra topic, that's an analysis topic. That, I think maybe for both the algebraic geometers and for me, that's a big part of the reason why this is an interesting question. Okay, the plan to solve this question is to try to make a clean splitting into a problem which is entirely about analysis and entirely about algebra. Let me explain briefly the 99%. There is a problem which I will pose in a minute, which is entirely about analysis, and its solution is going to be constructive. And so if you follow the constructive solution, you can do that using the most elementary computational algebra. And so the 1% arises from that remark. And the problem entirely about algebra, I shouldn't have written 99%. It's going to be 100% about algebra. Anyway, we're going to split our question into an analysis question and an algebra question. So here's the here's the analysis question. Given polynomials A1 through AD, don't think of little f as an unknown polynomial. Think of it as a C infinity function. And the problem is to characterize this C infinity function, the C infinity function's little f, for which our equation, for which the usual equation has a CM solution, capital F. Okay, that's the analysis problem. Let's go back to the example of Brenner, Epstein, and Hofster. So there's the example. Suppose now that little f is a C infinity function on R3. Which functions little f, which C infinity functions have the property that there are continuous functions, capital F1, capital F2, and capital F3 that solve the equations. And it's a nice little exercise to prove that a continuous solution exists if and only if the conditions you see in the box hold. So f and its first derivatives in x and y vanish on the z-axis, and the mixed partial with respect to x, y, and z vanishes at the origin. Okay, and that's necessary and sufficient for the existence of a continuous solution. It's rather strange, but true, that third derivatives of little f enter, even though we are only interested in finding capital F's that are C0, that are merely continuous. So that's a feature of the problem. Okay. Now, the solution of the analysis problem in the general case is the following theorem. So given polynomials A1 through AD on Rn, we can find finitely many linear differential operators with three properties that will be given in the next three slides. First, the first property just tells us what these differential operators look like. So each differential operator has the form that you see there on the slide. So it's a sum of, well, it's a variable coefficient linear differential operator. It's going to be acting on C infinity functions f, but it has coefficients that are semi-algebraic functions. And these semi-algebraic functions need not be continuous. We'll see in an example that they're not continuous. But nevertheless, this is well defined because we don't multiply by a discontinuous function until after we've taken the derivatives. So that's what each linear differential operator looks like. And so we exhibit finitely many such differential operators. And now here's the second key property of these differential operators. We want to characterize the C infinity functions little f for which our equation admits a CM solution. And the answer is that a C infinity function little f admits such a solution if and only if it is annihilated by all of those differential operators. Okay, and the third property is that we can compute the coefficients of these operators. That's where the algebra enters, where the 1% algebra enters, because the proof of this theorem is, the proof that there exist such differential operators is constructive, and so you follow the construction at each stage and do something sort of algebraic to produce the coefficients of our differential operators. Let's go back to the Renner-Epstein-Hochster example and see what these differential operators are. Well, there they are in the box. So this one means an indicator function. So the first of these differential operators is simply don't differentiate, take the function itself, but multiply by the indicator function of the z-axis. Okay. The next one is, or the next two are the derivatives with respect to x or y of our given function, but then multiplied by the indicator function of the z-axis. And the very last of these differential operators is the mixed partial dx, dy, dz, multiplied by the indicator function of the origin. And so a function little f is annihilated by those if and only if it is zero, its x and y derivatives are zero, all of that on the z-axis, and at the origin, the mixed partial is zero. And so the general theorem about these differential operators contains what I said about the little example of Renner, Epstein, and Hochster. Okay, I have no time to say anything at all about the proof of the above result, except I want to say that it is based on further study of Glaser refinements. So the Glaser refinement, the idea of a bundle and the idea of a Glaser refinement continues to be important for the study of these questions. Okay, finally, the algebra problem. Given linear differential operators in the form of that we just saw, but imagine that these differential operators are just given to you. They don't necessarily arise from the previous theorem. They're just, I pick them at random and I throw them at you. Okay, then the algebra problem is as follows. You're going to form an ideal in a polynomial ring, and the ideal consists of all polynomials which are not only annihilated by the differential operators, but have the property that if you multiply a given p by any other polynomial, even that is still annihilated by all the differential operators. From that definition, so I call that I of the operators L1 through Ln, or through L nu max, whatever. Given the differential operators, compute generators for that ideal. That's a pure computational algebra question having nothing to do with analysis. Okay, observe that if the polynomials that are annihilated themselves by the differential operators already form an ideal, then there's no harm in allowing ourselves to multiply p by q before applying the operators, and therefore the ideal of polynomials annihilated by the L's is precisely the ideal that I just defined. Okay, and so we have reduced matters to a problem of computational algebra, and if we solve that, then we can read off generators for the ideal of polynomials with the CM solution of our linear equation, because given a polynomial, it is a C infinity function. And so there's a CM solution if and only if the F is annihilated by all the L's. And that's true if and only if QF is annihilated by all the L's for any Q. And that means that the F belongs to this ideal. And our computational algebra problem says that, that we can exhibit generators for such. Okay, and so we have solved problem Q2. Now, problem Q3, I see that I'm out of time. Let me just say that we don't know the answer to Q3. I could tell you some special cases, but I don't know the general result. And so let me just skip all discussion of Q3 and thank you for listening. And the talk is over. So thank you.
Thank you very much, Professor Pfefferman, for this very inspiring talk.
Thank you.
So now we have time to maybe to make questions to Professor Pfefferman. So the system is like this. You can raise your hand, and then we can allow you to unmute, and then you can ask to Professor Pfefferman. Are there any questions or comments? It seems that people is very happy.
Okay.
With your talk. I have a question, but myself maybe.
Sure.
Maybe I don't know if my question makes sense, right? But what happens if instead of considering the CM functions, one consider, let's say, closed family of functions, like function in ICMAM classes with this rational regularity, or
okay, that is a very, very reasonable question, and I haven't the faintest idea.
It's very general.
It's
general.
I would say a very reasonable research problem. Yeah.
Thank you.
That's my short answer.
Someone raised their hand.
Yes, I have just a question about what is the base of the bundle E when you speak on your talk, please?
Okay, so it depends on the context. So let's say if you're talking about bundles in general, E is just any compact set. Okay.
Yes. And about the fibers, they are vector space or module?
Wait, I'm sorry, I'm muted. I'm sorry, you didn't hear me. Wait, let's start over again. Please start over again.
Yes. I am speaking about the fibers.
Yes.
They are vector spaces or modules?
Oh, okay. They are, okay. So the fibers are cosets of submodules. But remember that this module is also a finite dimensional vector space. So submodules are in particular, translates of submodules are affine spaces, but they're special affine spaces.
Yes, thank you very much. much.
Okay. Okay, more questions for Professor Pfefferman?
I think Patrick has his hand raised.
Professor.
Yes, I have a small question for you, Charlie. Thank you very much for this very interesting talk.
Thanks.
Let me start again my video. What about the case m equals infinity? So you are looking for functions f1, fd, which are C infinity.
That is a very, very natural question. I would guess that I would guess that the first question is solved sort of by work of Mather and Malgrange from the 60s. I would guess. I have not checked it in detail, but I would be surprised if that is not true.
Okay.
So on the one hand, C infinity is very, very natural. On the other hand, the ideas are we have very nice relations to algebraic geometry, but you are allowed to lose derivatives. And so if you are not allowed to lose derivatives, then it's a different game.
Okay.
Maybe that's the answer.
Thank you. So in some sense, the C infinity case is easier because of that. Yeah.
I would say it looks easier because it was attacked earlier. Who knows? If it were the other way around, maybe one would say that the CN case is easier.
Okay, thank you very much.
Sure. Okay. Now let's see. I saw 2 hands raised, but on the other hand, there were 2 questions. Are there any more questions? Okay. Well, I see a thank you in the chat. You're most welcome.
Duan, you're muted.
Am I muted? Hello?
Okay. No, thank you for accepting our invitation. Just let me add that there are many somehow young researchers from Latin America, and this is somehow very important maybe for to get inspired to do mathematics. So thank you very much for this.
All right, well,
okay, so
thank you.
Thank you. Okay, so yesterday we had a change in our program. It seems that today, after the Professor Pfefferman's talk, we will have the talk of Professor Nikolai Sekop from France. And let's see if Professor Sekop already is able to join us in the virtual room. Okay, he's here. Brian.
Hello.
Hello, Professor Nikolai.
Hello.
How are you?
Fine. So maybe I can give my slides, okay?
Yes, thank you. Please, could you start sharing your screen? Excellent. Excellent.
And now I just put it in the... Okay, so do you see it now?
Yes, Professor Sekop.
Okay, so maybe I can start. Is it okay now to start?
Yes, just then let me introduce you. So it's my great pleasure to introduce our second speaker of this second day of conference is Professor Nikolai Sekop from INES Lyon at France, who will talk about new non-degenerate invariant measure for the Bayesian-Minono equation. So thank you very much, Professor Sekop, for accepting our invitation, and you can start.
Thank you very much. I just have a small problem. Yeah, okay, now it seems okay. So do you hear me?
Excellent. Yes, we hear
Yeah,
you
you
very
can
well.
hear me. Okay, good. So I would like to thank you for inviting me to give talk to this conference. And actually, I will present some very recent result on invariant measures for the Benjamin-Ono equation. And actually, this is a very partial result. And since you told me there will be many young people, I would like to advertise that there are many open problems in this around this result. And so hopefully this may be of interest of some of you. And also I would like to mention that what I will discuss today is very close, I think, to the talks by Patrick Gérard and Monica Vichan. So all these talks are related to integrable methods in dispersive partial differential equations. So one may say that in recent year, we improved a lot our understanding of integrable models. Even if the integrability of equations like KdV and so on is very old subject, there were great progress around the years, I don't know, 1970 and things like this. Actually, in recent years, thanks to work of people like Monica Vichan, like Patrick Gérard and others, there is a great progress, which somehow was not clear before. And also many new questions were asked in this field, somehow motivated by the progress in dispersive PDE in the years 1990s. So somehow two fields met, and there are very nice intersection. And I think people like Patrick Gérard and Monica Vichan did really great work on these problems. So what I discuss is really in this line of research, and I would like just to present some partial progress, and hopefully, as I said, this will motivate some further research. So the problem I would like to study today is the problem, the Benjamin-Ono equation. So the Benjamin-Ono equation is written here. So it's a first order in time equation. This is a dispersive equation. I will explain why I call it dispersive, because there is a kind of dispersive operator. I will explain why I call this dispersive operator. So as you see, it's an evolution equation, and in the left-hand side, there are two terms. One is a linear one, which is h dx squared u, and the other is the nonlinear one. And so we are interested of the Cauchy problem, which means that we prescribe the initial data. And in fact, our functions are real valued. Even if I don't say it explicitly, the function u is real valued. It's not complex valued like for the Schrödinger equation. It really takes real. Now it's with the values in the real numbers. It's periodic in space, and so I see that it's time reversible. So this equation is time reversible. It's really completely different from the heat equation, which would be there if we forget h. Then the problem, as you know, the heat equation, even the linear heat equation, is not time reversible. It's strongly ill-post for negative times. Here, this h makes the job of making the problem time reversible. And somehow this is important. And so this h is the famous Hilbert transform, which on periodic distributions can be defined either as a singular integral operator, but it can also be defined on the Fourier side as via the Fourier transform. So it's simply the Fourier transform of the Hilbert transform. For positive values of n is minus I, the Fourier transform. But for negative values of n, it's I, the Fourier transform. You know, it changes the sign in positive and negative. So this change is very important. And at the zero coefficient, it just gives zero. And so this h, in fact, has a property very much like the multiplication by I if I allowed complex numbers. So we can see that if I apply twice h, I obtain minus identity at least if I act on functions which are with zero mean value, with zero Fourier coefficient, which means zero mean value. So it's easy to see because the square of minus I sine is -1. So sine square is 1 and minus y square is -1. So somehow h square is doing the same job as the multiplication by a in the scalar case, but h somehow is not a number, it's an operator. And this is the price to pay if I would like to stay with real valued functions, because as you see, u is, even it's not written on my slides, u is real valued. And in the layout of real valued function, we cannot put a number which make this equation dispersive. So we are really obliged to put this operator. And so once we understand this, somehow we see that the evolution of exponential tx dx square is very different from the evolution of exponential t dx square, which is the evolution of the heat equation. If I didn't have h, you see they are very close to each other if we see it like operator, but this h makes that the problem is time reversible, and so it behaves very much like the Schrödinger equation, because you can think of this h like multiplication of I, and as you know, many things of the Schrödinger equation, it's a dispersive equation. By the way, you can make this connection even closer if you decompose your initial data on positive and negative frequencies, and then if you make this decomposition, simply in positive frequency we will have one Schrödinger evolution, and on negative frequency another, just we change the sign in front of the dispersion. So why I make all this introduction is to say it's really different from the analytic viewpoint, the heat equation and the Benjamin equation. On the other hand, written like this, we see that there are a lot of algebraic similarities. So each time we make some algebraic computation around the heat equation, we may think that maybe in the Schrödinger, in the Benjamin equation, similar thing would work. And so this philosophy was used by Terence Tao when he discovered what we call the gauge transform for the Benjamin equation. Somehow, maybe you know that for the heat equation with this nonlinearity dxu square, there is the so-called Hopf-Hoh transform, which reduces the heat equation with nonlinearity dxu square to the linear heat equation. So it's really a remarkable transformation, which just says, okay, I have the heat equation with a nonlinear term, and I have a transformation which kills the nonlinearity. So this transformation is, of course, very important. For instance, it's used for KPZ equation and other recent work on singular stochastic PDE. But for the Benjamin equation, is there something like this transformation? And it turns out that yes. And this is what Tao did. He said that, okay, maybe I have this H here. Still, I can try to do some transformation at the level of the equation. Maybe I will not completely kill the nonlinearity, but at least I will kill the most important part. And that's what he did, and what nowadays is called the Tao gauge transform for the Benjamin equation. So in a sense, I just would like to emphasize that even if analytically the Benjamin equation and the heat equation are quite different, from viewpoint of algebraic viewpoint, they have some connections, and somehow we can do these algebraic computations from one side to simplify the equation, and then of course we should forget that it is not the heat equation and do some dispersive analysis. So it's really what Tao did, and it was very surprising at the time when he introduced his gauge transform. Okay, but as you maybe saw on talks by Patrick Gérard, we will see Patrick Gérard and his collaborators understood even how to use better the algebraic properties of the Benjamin equation. And it's really amazing. Okay, so let me now talk. I'll be interested on invariant measure for Benjamin equation in my talk. And let me first recall the Cauchy problem theory for this equation. So I will consider the equation with some initial data, which I will suppose on the Sobolev space HS with some zero below. So this zero is not like the zero in the zero Dirichlet boundary condition. So this zero would like to say something else. These are the functions or distributions such that the zero Fourier transform is zero, such that the Fourier coefficient n is the complex conjugate of the Fourier coefficient minus n, right? So under this assumption, we are sure that U is real valued. And so this space HS0 is endowed with the norm, the usual Sobolev norm. So just the sum of the squares of the Fourier coefficients times some weight, which is n to the power 2 times s. And so as you see, since it doesn't touch 0, I can put really absolute value. And so bigger s is, stronger this restriction is, and so smaller the space we obtain is. So this s really measures the regularity. How regular is our function? And so if you would like, if you impose that this sum is finite, more s is, more we ask on our function. If I take s equal to 0, I just recover the L2 space by partial identity. And so this is the norm in the Sobolev space HS0. So what means this 0? So there are two ways to see. If we suppose that the 0 Fourier equation is 0, this may be seen in the physical space as imposing that integral of u is 0. And so it's not a problem to suppose this for the Benjamin equation, because if you look at the equation, if I integrate the equation, the xu square is formally of integral 0, and the x square u, h is not a problem. It commutes with the x square. In the Fourier side, it's just the two are Fourier multipliers. So also formally of integral 0. So at least formally, the mean value is conserved. So if I suppose that initially the 0 coefficient is 0, it will be 0 forever. And so I just may study the equation on this space. It's preserved by the nonlinear flow. As you see, a linear space is conserved by the nonlinear flow. So it's not so obvious, but it works. And so this is a natural space. And let me just comment that you can just see that the 0 Fourier coefficients is at least formally equal to integral of u. So it's the same. Of course, what is nice is that when I write u hat 0 equal to 0, I'm not even supposed to know that the integral exists. I can say it even for periodic distributions. Why, when I write this notation with integral, well, I should explain why this integral is there. So it's really better for me to write u hat 0 equal to 0. And so I hope that this discussion convinced you that this HS0 is a natural space for studying the Benjamin-Ono equation. Okay, let us now go back. So if you didn't like this 0 constraint, actually the result we present have natural analogs if we take the spaces where the 0 Fourier coefficient instead of being 0 is alpha. So if you do this, it's still preserved by the flow, this space. And actually, by making a small change of variable, you can reduce the matters to 0 coefficient being 0, and just to add a harmless linear term in the equation. So really, at least from my viewpoint, Benjamin-Ono equation is like this. It leaves invariant all these spaces HS alpha. So alpha can be any real number. It's a kind of foliation. So for each alpha, there is a flow, and this flow don't see each other. Somehow, there is a foliation on the space HS, such that on each part of the foliation, the Benjamin-Ono flow is invariant. And so if you understand it on one alpha, you understand it for all others. For that reason, I will suppose in the sequel that alpha is 0, and my Fourier space will be there. So the Cauchy problem for the Benjamin-Ono equation has a rich history, and it maybe started with the, I think this is a very old result now, maybe 44 years. So in 1979, it was proven that for every HS where S is bigger or equal than 2, there is a unique global solution of the Benjamin-Ono equation in the space HS0. So this 0 is just to say that the 0 mean is 0. And moreover, it's really a well-posed problem. The dependence with respect to the issue that is continuous, and there is a uniqueness in this class. So this is a very nice result, which uses two things. One of thing is the Kato iteration method for getting global solution, local solution in time, local. And so at that time, it was very new. Kato invented his quasi-linear scheme at that time. So it was somehow application of very recent ideas at that time. And also you have the global where posedness, which results from some miraculous conserved quantity for the Benjamin-Ono equation. So in 1979, it was really not clear. Of course, they discovered somehow in experimental way the conserved quantity, but only the recent work by Capeller-Gerard and Capeller-Gerard-Topalov explained where these quantities really come from. Actually, and not, okay, it was known before the Lax pair, but it was really put in some analytic framework only recently. But at that time, already the algebraic part was done. As you see, sometimes algebra is quicker than analysis. And so at that time, this algebraic part gave some information to Jean-Claude Tussaud to globalize the solution. Okay, so this is the basic theorem. And this flow of the Benjamin-Ono equation on regular space is already very nice. And so I call it phi1. Phi1 is the map which to any initial data in HA0 gives the solution at time t and HA0. So this is the map phi1t. And now, once we have this result, the question is whether we can extend this flow to lower regularity spaces. This was the history of the Cauchy problem. And then there were many contributions, including the one by Tao with the gauge transform I just discussed before. And well, I will not say all results. I just say the strongest results, which is in 2020, as you see, 41 years later. So now we can relax the assumption as being bigger or equal than 2 to the restriction as bigger than -1/2. So as you see, and so what is the statement proved by Gerard, Capeller, and Topalov in 2020? They proved that the flow map phi1 of Benjamin-Ono only defined on regular spaces has a unique extension to the low regularity space HA0, such that in addition, this extension is a big continuous bijection on HA0. So you have really what you want. It's well defined. It's a bijection. You know, it just sends the set to itself. It's in a sharp contrast with heat equation, where no such bijection is there. You know, in heat equation, somehow the phase space becomes smaller and smaller. If you start from some it becomes much smaller in the positive side, and the negative side you cannot even define it. Or if you want to define it, you should go to something really not possible, right? Anyway, so here it's really bijection. So really the flow of a dispersive equation is really bijection on this kind of HS spaces. Well, and this result is optimal in the sense that we cannot hope to extend it below -1/2, at least deterministically. So in the end of my talk, I will explain that I have some hope to extend this result even below -1/2 by using probabilistic ideas, which is somehow something which is also active area of research. Well, so this is now the best possible result on the Cauchy problem. And let me just say that it was used by using integrability methods. And in fact, I imagine that the talk by Patrick will explain you about this result. But what I would like to emphasize is that it was really used using integrability methods. Previous to the work by Gerard, Capeller, Topalov, there were many results using, I would say, non-integrability techniques. And so the best result by these methods is in this periodic setting is a result by Luc Moulinet, which is based on the Tao gauge transform. In fact, Tao introduced his gauge transform, which is the analog of this Hopf-Howe transform in this equation, in the case when the equation is posed on the real line and not in the periodic setting. But of course, it's a highly non-trivial task to go from the R case to the periodic case. And so Moulinet did this task, and by this method of the gauge transform, he obtained the result of theorem 1, but only for s bigger or equal than 0. And if you would like to go to negative indexes, we don't know how to do it without exploiting integrability of the equation. So, and it's natural. There are many situations. The best result we can do is by integrability methods, and we have no idea how to do it by more general methods, let's say. Okay, but in this talk, I will study another problem, which is the problem of invariant measures for the Benjamin-Ono equation. So what does it mean? So let us, here is the definition of invariant measure. So we say that a probability measure on my space, HS, the place where the flow is defined as bigger than -1/2, is invariant by this flow phi1. So phi1 was the flow of KdV. If it has the following property, you take some set A, which is a subspace of HA0. So this A is a set of infinite dimensional space. So you take it a Borel set. It means that it is in the sigma algebra generated by the open sets. So you take such a set and you transport it by the flow and you obtain another set. And so if the transported flow by the flow set has the same measure as the initial set, then you say that you have invariant measure. And in another way to write this property is that for every test function, which is only in A1 with respect to the measure mu, you can write that the integral of the function of the flow with respect to the measure is equal to the integral of the initial data of function with respect to the measure. It's a kind of conservation law, you know. These kind of quantities, integral f of u, are independent of time. So of course, two definitions are equivalent. Well, the second implies the first by just taking the A1 function, the characteristic functions, and on the other way, you just use that these characteristic functions are dense in A1, and then so you can go from first property to the second one. And so this is the what I call invariant measure. So invariant measure infinite dimensional space is very, very delicate thing, especially for dispersive equation, because it's not clear that such object exists. And also it's in infinite dimensions, there is no canonical measure. You know, in finite dimension, the Lebesgue measure is somehow considered as canonical. And often you very quickly enter in the world of the measures absolutely continuous with respect to the Lebesgue measure, and in the end, you even forget that your problem is about transport of measures. So, for instance, when you write the equation, the say Vlasov-Poisson equation or whatever, at the end, everybody thinks that it's an equation for some real valued function of integral 1, but in fact, the problem is not for function; it's for measures. But somehow, very quickly, you say, okay, the only measures I care about are absolutely continuous with respect to the Lebesgue measure, and then the problem is about the density. And then, okay, of course, no longer we talk about measures. In infinite dimensions, you don't have something like this. You just don't know what is the analog of Lebesgue measure, and then what you can do is you at least try to see measures which make things which are measurable, in the sense that if initially I have so this A, you can see it as some event initially, but not only one data, but many data. So if you find a measure such that you can measure simultaneously in time 1 and time later than 1, you are happy, because you know that if something is measurable at 0, it's also measurable at later time. And if you are happy, it's really the same measure. So this property is really exceptional for Hamiltonian equation in infinite dimension. And so this is one of the interests of having such kind of invariant measures. And there are many others. For instance, you can apply recurrence theorems and so on. And also from mathematical viewpoint, it's really a challenging problem to find such kind of invariant measures, because usually if you take some arbitrary measure in infinite dimensions, the transport by the flow will certainly be singular with respect to the original one. And by the way, in finite dimension, it's not like this, unless you suppose you are absolutely continuous with respect to the Lebesgue measure, but certainly you can take a crazy situation. But somehow the Lebesgue measure is canonical. Okay, so this is just to motivate. And how we can construct. So it is well known that we can construct invariant measures each time we have conservation laws, or what I call first integrals. And so this I worked during several years together with Nicola Vichilia and also with Yu Deng. So we worked on this kind of problem, exploiting conservation laws. As I said, conservation laws of Benjamin equation, or some of the conservation laws, were known since long time. And so it turned out that there are some, for each half integer, there is a conservation law with leading term, the HS norm that I defined in the first slide, plus some small order correction. So there are such conservation law. And so with Nicola Vichilia, we proved that one can define this probability measure, which is formally given as exponential minus the conservation law times the Lebesgue measure on function. So both things don't make sense. du in infinite dimension doesn't make sense. And this is infinite, in fact. And at the end, what happens is they compensate and they give a well-defined measure. So this is a highly non-trivial statement. So we wrote several papers to prove that these measures are well-defined. And not only they are well-defined, but they are absolutely continuous with respect to some explicit Gaussian measure, which is written here, which is given by this map, which to some omega gives this random Fourier series. Well, what this map does. So you know that random variable is just a map from some abstract probability space to the real numbers. Real are random variable. So this is like the real random variable, just the difference, and the huge difference is that the real numbers are replaced by the space of functions. As you see, for each omega, I don't give a number, I give a function. Well, so what happens is that by doing this, instead of having the law of such a random variable, instead of being a measure on R or Rn, as in the usual probability courses, now it's a measure on the infinite dimensional space, Hs. On which one? Well, it's not maybe so clear why, but it's actually a measure on a lower regularity space. You know, I start by conservation law, which is Hs, and I try to define this measure, and then the resulting measure is not on Hs, it's on H sigma, which is 1/2 regularity smaller. Well, it's not so surprising if you have some experience with Brownian motion, because if I do the same thing for the Brownian motion, here the space will be H1, and then, as you know, Brownian motion with typical regularity, not H1, but H1/2 minus epsilon, or even C1/2 minus epsilon, but you cannot take one derivative of the Brownian motion. So something like this happened with this measure μs. Okay, so we proved this thing, and actually during 2000 and 2015, in joint efforts with Vichilje, but also with Hudenk for some of the work, we obtained that there is an infinite sequence of invariant measure by the Benjamin-on-off law. And so, well, it was work which didn't use integrability of the equation. In some cases, the analysis was quite involved, but somehow we completed the program, each known conservation law with this leading term, which is Hs square. We could define the measure, and we could show that it is indeed invariant under the flow. And in that time, we didn't have the Kappeler to power of Gerard result, but already with the existence result, we could construct the flow. And so this was something I did between 2010 and 2015. Then other people generalized this result to other equations, like, for instance, Genovese and Luca Valeri obtained similar result for the derivative nonlinear Schrödinger equation. And so I stopped working on the time, but recently the works by Kappeler, Topalov, and Gerard appeared. And so I asked myself, well, whether we can use these works to say something new about the invariant measures for the Benjamin equation. So since 2015, nothing new happened. And actually, relatively easy, we can make a first modest step in this direction. So this is the result I would like to present today. Well, here is the statement. So this paper is available on arXiv maybe 5 months ago, and you can see it. You can see it. If you have questions, don't hesitate to ask me an email or something like this. So we've put ourselves in the regularity assumption of the paper by Gerard Kappeler-Topalov, and then we prove that there is a probability measure on the Hs space, which is invariant under the flow of the Benjamin equation used constructed by Kappeler-Topalov and Gerard. And it exists. But what we know about this measure? We know that this measure is somehow non-degenerate. That's part of the title. What I call non-degenerate is that this measure has the property that every full measure set is dense in Hs, right? So it means that, in particular, the measure charges every open set, right? So it cannot be somehow a measure which is really isolated on one point or some small part of the Hs. It's really everywhere in Hs. It charges every open set. So somehow it sees all functions on Hs. And also, there is no cheating. It's really low regularity measure in the sense that if you take slightly higher regularity, the HS, the more regular spaces of measure 0. So this measure really lives on HS and nothing more. If you accept slightly more regularity, then the measure is 0. So it really lives on functions with regularity exactly HS. And so, well, if you take this result for s equal to -1/4, but if you take any number between -2 and 0 is the same, -1/8 or whatever, it's new and was completely out of reach before. You know, the works I mentioned with Vichile and Denk, we were absolutely impossible for us to prove this kind of result. But now, after the work of Gerard Kapper and Topalov, maybe I make a mistake, J keep T, not P. It is possible. And in fact, this shows that the result is new, really new. But of course, if I should say what makes for this result, it's really the paper by Gerard Kappeler and Topalov, which enabled us to do such kind of results. So let me mention other works on invariant measure are the works by my former student Muhammad Ussi, who used the dissipation fluctuation method by Cooksin to show that there are invariant measures in infinity. So there are other works. The problem with these measures is we have no idea how much they are non-degenerate. For instance, this property that every full set is dense, we don't know how to do it, and we are not only don't know how to do it, we have no idea how to do it, and we are very far from knowing how to prove it. This is somehow the disadvantage of this dissipation fluctuation method in the context of Hamiltonian equation. So this method is very nice for parabolic equation, gives really nice, but for dispersive, it really makes it's not clear how to use it in an intelligent way in order to say more about the invariant measure, and if possible. And then I would like to emphasize that much remains to be understood. That's why I've chosen this talk, because I think there are really many problems. In particular, I don't have this result doesn't give alternative proof of the results between 2010 and 2014, but it is likely they can give it. The method I use, just one should sit down and do some work. I'm completely convinced that we can reprove the result we already knew and even do more. But for the moment, it's not done. But okay, it's maybe too complicated. More easy results. I think this theorem is also available for other integrable equations. For instance, for KdV, for DNLS. There are other equations where you have the structure of action angle variables I will describe in the next slide. And for all these equations, this result should be true. Of course, things should be checked, but I'm convinced that they work. Even if I didn't write it in my paper, I think it's possible. Then, of course, for each model, the same problem. Can we say more about this measure rho s? Of course, already I say a lot. It's non-degenerate. But can I say more? Can I really say something about what it is like? I think it's possible if one works more. So these are really many open questions, and I think some of them are not so difficult, others are more challenging, but yeah, I think it's not the last result on this subject. Okay, so let me in the remaining I have 15 minutes, right?
Yes, Professor.
Okay, so in the remaining 15 minutes I try to explain a little bit the proof. So the proof of this result is based on the Birkhoff map introduced by Kappeler, Topalov. And so what does it mean? So it means that in order to write the Benjamin equation in the original way, we will introduce new coordinates, and in the new coordinates, it will become much simpler. And so everything will be hidden in the transformations which go from one coordinate to another. So let us explain what does it mean. Maybe Patrick Gerard explained this in his talk, or we will explain. I don't know whether his talk already passed. So by definition, the natural number for me are 1, 2, 3. So it's important to say because in France, we also include 0. We denote by HS the set of sequences of complex number such that these quantities, so very much like the Fourier coefficient, but I don't say Fourier coefficient, just the set of sequences. Well, if we write Benjamin-Ono equation in Birkhoff coordinates, then the Benjamin-Ono equation on the space HS minus 1/2 becomes a kind of ordinary differential equation on the space of sequences HS. You know, I pass from S minus 1/2 to H, small hs. When I put small h, it's really the sequences. And so the sequence should satisfy this ordinary differential equation with infinitely many unknowns, right? So it's still an infinite dimensional system, but of course there is no miracle. If you start by infinite dimensional system, the new one should remain infinite dimensional. Otherwise you lose some information, right? And so it turns out that solving the Benjamin-Ono equation in HS minus 1/2, it is essentially the same as solving this ordinary differential equation, which is much simpler. If you think a little bit, you see that you can solve it really explicitly. But of course, not the solution is explicit formula, but not so trivial, because as you see, you have this sum between k and infinity of ck squared. This minimum, not so important, because each time you put n, starting from some point, this minimum will be actually n. And so this sum is at infinity behaves like the sum of zk squared. So as you see, if the sum of zk squared is not well defined, you have problems to solve this equation because this degenerates somehow. Okay, so that's why the limit for solving this equation is L2, small L2 in HS. And as you see, there is a shift. You go from S minus 1 to S. So if L2, so the small L2 is the limit in that place, the limit on the other place will be minus 1/2. That's why the restriction was S bigger than minus 1/2. Okay. Well, so that's the point. So if I can go to 0 here, here I can go to minus 1/2. And so the result by Kappeler, Topau, and Gerard can be replaced like this. If we note the phi t, you know why from the very beginning I was with phi 1 for the Benjamin, because phi t will be the flow of this equation. So what they proved is that if you take phi t the flow, then there is a map, the so-called Birkhoff map, which is a totally nonlinear map, which sends HS, where the Benjamin-Ono equation was written originally, to the sense of sequences with 1/2 derivative more somehow, which is a bicontinuous bijection, and which makes that one flow becomes the other modulo the conjugation with this Birkhoff map. So finally, you have this connection by this map phi. And this phi is a continuous map, and that's at its bijection. That's what I will use in order to prove my result. Okay, so let us now see actually what I will do. I will write a measure on the action angle variables, and just I will send it back to the original space, and my result will be proven. In the action and the variable sides, the measure will be totally explicit, and I explain how to do it. So just take a probability measure on R2, which is defined as a measure absolutely continuous with respect to the Lebesgue measure on R2, multiplied by some density, which is a radial function. So it's extremely important that this is a radial function. But the only thing we suppose is that it's radial. So essentially, you take some radial function of integral 1 and you multiply it with the Lebesgue measure. That's my measure theta. What is important is theta is invariant on the direction of the rotations of R2. This is very important for me. And I also suppose that it has finite second moments, which means that if you multiply by the weights x squared, y squared, it's still integrable. For instance, you can take the Gaussian, but you can take any function f which is radial, and which has this, which is integral 1, of course, and such that this integral is finite. Well, now I take a sequence which is defined like this, 1 over ns plus 1 over logarithm of n1. So this sequence, Cn star, zeta n star, has the property that it is in Hs plus 1/2, but it is not in H sigma for sigma bigger than S plus 1/2. As you see, it's really the second non-degeneracy property. Well, you can just check it's true. It's a small computation on sequences, because if you take the HS plus 1/2 norm of this, you just recover the series sum 1/n log of n square. And this is a good exercise for students. This converges. But if you put sigma more than 1/2, this logarithm no longer saves you. You just have a strong divergence of the series. Wow. Okay, I define like this. And then I define a measure on my space HS plus 1/2, which is the image measure between omega, and on each side of the sequence, I put this coefficient time g and omega, where g and omega are identically distributed with respect to the measure theta. I hope I said it on the previous slide. Yeah, g and omega are identically distributed with respect to theta. It's really not the Gaussians like in my work with Vichilia and Denk. And then there is a proposition saying that the measure mu on the level of the sequences is invariant under the transformed Benjamin-Ono law. Well, it's not obvious, but it's not so difficult to prove. One uses the Hamiltonian structure of the equation. One uses the radial assumption on my functions f defining the measure theta, and it is relatively easy computation. That should be done, of course, but it is done. I will not do it. And then one can just simply say that the measure on the side of the original, back to the original coordinates, is simply the measure of some set S is simply the measure on the sequences of the transported by the Birkhoff map of subset A, where A is the measure on edges. Here is my invariant measure. So let us check that this invariant measure has all the properties. First, it is invariant by definition, because if you take the rho S of phi1t, phi1 was conjugated between phi minus 1 and phi. And so then just one phi simplifies, and you have mu of phi t phi a. But then I proved on the previous, as announced in the proposition on the last slide, mu is invariant, phi t is invariant under mu, so I recover with mu phi a, and then again I use the definition and it is invariant. So it shows that rho s is invariant. It's essentially by definition, and then the conjugation. So okay, I define the measure which is invariant, but now I should check that every dense set is every set of full measure is dense. So we have invariance. Why this? Well, this is true because if I take a measure of full if the measure is full with respect to this measure, then then the image under phi of this set is a full measure with respect to mu. Then the whole job, and this is done in my paper, I don't have time now to solve, is that mu has this property that if a measure is if a set is a full measure, then it is dense. So we have that phi of A is dense on the level of the sequences. But then we know that it is bijection and it's continuous. And so the set A, I just can write it as the inverse. So this is a continuous map of phi of A. And so it's again dense, because if you take a dense set by a continuous bijection, it's again dense. It should be bijection, because imagine the constant map. It's not a bijection, and dense set is not to dense set. But if you know that it's a bijection, dense set is surely set to a dense set. It's a small exercise on continuous maps. So that's the why I show that full measure set on the level of the sequences goes to full measure, goes to dense measure, to dense set on the level of the Benjamin-Ono. As you see, I use two things. The first thing is that bijection, continuous bijection sends dense set to dense set. And I also use that it is a continuous map, thanks to the work of Capeller, Gerard, and Topalov. Okay, and then the last property is written here. If I take something bigger than S, well, if I take the measure of this set, I said that this is 0. Well, again, it is the measure of the map. And then it is equal to because it's a bijection, this is the mu measure, the measure on the sequence of H sigma plus 1/2, and this is 0. Well, it's another computation to be done. It's not so obvious, but should be done. It's written in the paper. And here, to make work this computation, I really suppose this fact that Cn star is not in H sigma plus half. I gave you a concrete sequence doing the job, but any sequence which do this make that this property that the mu measure of H sigma plus half is 0. And so essentially we proved the theorem. Well, in the 5 minutes we had, I would like to say that actually on the level of the sequence, I can even extend almost surely by probabilistic methods the flow phi to L4. So far it's defined on small L2, but I also defined on L4. So if you take a sequence such that the small L2 norm is infinity, because if it is finite, the flow phi is defined. But if it is infinite, I, however, suppose that with the square is finite. Okay, it's weaker assumption. You can have a sequence which is like this, but not like this. The typical one is 1 over square root of n. So the first is infinite, but the second is, of course, finite. This is the main example I care about, 1 over square root of n. This is what corresponds to the white noise, together with Gaussians. And what I say is that for this data, for instance, alpha and 1 over square root of 1, I can define almost surely the map on the sequences. Well, I really don't have much time. I should suppose a little bit more on my function. I should suppose that the 4 moments are finite. I still define the image measure on the sequences like this. Now it's no longer on HS. It's because the measure of H0 is 0, but using some small inequality, it's a measure on H minus 1. It's still a Hilbert space, some larger space. And so you can see this image measure as a measure on this space. And then what we have is that now if I try to solve the equation on the support, it's not possible because these L2 norms diverge. However, we can make converge the phase of renormalization. So something renormalizations are some tool which is now well understood in the field of PDE, of stochastic PDE. So I make renormalization in the phases. And so what I should say is that, okay, I know how to solve the truncation of this system. And the statement I prove is that if you correct the phases by some divergent constant, then you can make converge the phases and therefore solve the equation. But the only price to say is that in the finite dimensional approximation of the equation, you add this exponential 2 times TEN CN sequence, which is really divergent, strongly oscillated. So there's the only thing to correct to the sequence which defines the solution is to make what we call renormalization, multiply with strongly oscillating sequence. And so this converges mu almost surely to something. And so this something, I would like to call it solution of the equation with this very low regularity data on the level of the sequences. Okay, I know I went quickly because I don't have time, but I just would like to say that what I did is that even below the Kappeler-Topalov Gerard framework, we still can solve the Benjamin-Ono equation written in the Birkhoff map coordinates. What is missing is to see how this renormalized dynamics is mapped to the original equation. And so here we have no tool, because the tools by Kappeler, Topalov, and Gerard just say how this map works on L2 sequences. My sequence is slightly below L2. So there is one should develop more the tools of integral system to understand how they are transported. And if I succeed to do this, but we will solve Benjamin-Ono equation almost surely even below the H minus 1/2 threshold of Kappeler, Topalov, and Gerard. So I have a hope that, as I did it for many other models, that by using this probabilistic argument, I will even go beyond the optimal deterministically result by Gerard, Topalov, and Kappeler. Simply, I will use what is missing. So I think that what I explained already totally supports such a conjecture. On the Birkhoff coordinate side, we know how to solve it. That's what my last proposition says. Now there is a job with the Birkhoff map to go to the original ordinates and say, what does it mean? I am convinced that it will produce a flow of the Benjamin-Ono equation and even a new invariant measure, even below the best result. And so this is something we already did it for many other equations, especially in works with Nicolas Burck, but I have a hope that we also do it for the Benjamin equation, but it's just a question of time to do it. And so I just would like to say that what I did for Benjamin equation can be done for many other equations, for KDV, for derivative nonlinear Schrodinger equations, for nonlinear Schrodinger equation, cubic in 1D. So in many cases, we have the extra number of variables. So we just would like to, we should choose the best situation where we can understand how we can come back to the original ordinates by probabilistic method. So I don't know which is the easiest model, but I think that this line of research will have developments in the years to come. And of course, I encourage you young people to study this kind of course. And I think I'll stop here.
Okay,
Thank you
Professor
very much.
Lekov, thank you very much for your very nice talk. Okay, so very additional to the talks of yesterday of Professor Villan and Professor Gerard, this very nice idea of this specific question. So, are there any questions for Professor Lekov? Professor Gerard?
He's there, Professor Gerard.
Yes, I'm here, Nicola. Yes. Thank you very much for your talk. I had a question about the very last part,
Sure.
which corresponds to this nice renormalization.
Sure.
Maybe more comment than a question.
Sure.
Could you come back maybe to this part, and in particular to the formula for the renormalization on the alpha ends? Yeah.
Yeah, it is here.
Yeah. So yes, it seems that this renormalization at the level of the coefficient alpha n is just a multiplication by e to the I n something. Is that correct?
TNCN.
Yes, TNCN. But this
Modulus 1, complex number of modulus 1.
Yes, but what I like is this n, because small n, okay? Because it corresponds for our Birkhoff map to a translation.
Okay.
So if you multiply the vector alpha, the sequence alpha n by e to the I n v for some real number v, this corresponds to translating on the phi part, on the u part, to translating x by v. So you replace u of x by u of x plus v.
Okay.
So in some sense, that would mean that you translate your solution of Benjamin-Ono by some vector which is proportional to t, and also to something which is very big, which will...
That's exactly what I expect, that the renormalization can be written like this as a translation in the x variable by something which is very strong. Yeah, I maybe didn't insist on this, but that's what I expect indeed to be the final result. So I think that at the end of the day, if we believe that to the intuition I have, at the end of the day, you will have the true solution of the regularized Benjamin-Ono equation. And you just take in the x variable a slide, strongly, you make translation with some divergent constant times t, and then there is a limit. That's the hope.
So yes, I think the hope is good, and at least our computations on our properties of our Birkhoff map is really completely coherent with this. That was my comment.
I think it's only a question of time that somebody proves this.
Thanks a lot.
Okay, thank you very much. Are there more questions for Professor Nikolai Smekov? Maybe I have a comment, more a philosophical comment about, because I remember these works of Bourgain about techniques from analytic number theory to prove well-postness for KDB, for NLS Schrodinger equation, and so on. So my question is, okay, from there he worked with KDB and so on, and usually I heard from you and from Professor Gerard in other talks that you expect for KDB, also you expect for Benjamin Ono, but here you mentioned the opposite, that you expect for, that you do for this Benjamin Ono equation also applies for KDB and other equations. My question is if those techniques of analytic number theory also can be combined with these probabilistic methods or...
Well, usually these techniques of number theory, they are used for proving triggered estimates or kind of dispersive estimate. But in fact, what happens is that now many of these estimates can be proved without number theory because of this Demeter-Bourgain method. So what really is needed, let me say, it's if you don't need scale invariant estimate, no number theory is needed. The only case is number theory is needed if you want to prove some AOP estimate with data which is on the scale invariant level. Then there is a very nice work by Vishan and co-author and Kilip, where they prove these estimates. And so I think, of course, they combine with Bourgain-Demeter business. But if you don't need scale invariant estimates, the triggered estimates can be proved by this decoupling method of Bourgain-Demeter. So somehow, in his last works, Bourgain succeeded to kick out the number theory, but still we need number theory for scale invariant problems, scale invariant estimates. That's my understanding. So, well, my answer is that number theory is not so much needed now. The most efficient tool in this type of dispersive estimate is the decoupling theory of Bourgain and Demeter. Demeter wrote a whole book on this subject. So if you don't need scale invariant estimates, you just use decoupling, and they prove the most powerful estimates. If you need scale invariant estimate, you just take the non-scale invariant and you do some additional trick, which indeed requires some number theory like minor arcs and things like this, but only on this critical level. That's my understanding. And then this is for linear triggered estimates. Then on the level of the multilinear triggered estimate, I don't have such clear understanding. Maybe there are situations you still can use something in number theory which cannot be deduced by decoupling. This I'm not sure. But on linear level, I'm pretty sure what I say is true.
Thank you very much. Okay, so are there any questions for Professor Nikolai Sekop? Okay, if not, it seems that the participants are happy with your talk. So thank you very much for accepting our invitation.
Thank you for the invitation. And I apologize for yesterday, but as you know, it was not really my fault.
Yeah,
right?
yes.
Okay.
So,
okay, I wish you a very good continuation of your workshop.
thank you very much, Professor Sekop.
Bye.
Bye-bye. Okay, so exactly at this moment, we will have a 1 hour break. So you are able to take your coffee or a small lunch, I suppose, in Colombia or in Brazil. See you at 5 p.m. in Central European Summer Time. We will continue with the talk of Professor Iraine Sabadini.
Hello, Professor. Are you hearing me?
Hello, how are you?
Fine, it is a pleasure to meet you.
Aspetta, devo usare il salvascrivere.
We are going to start in about 2 minutes. Maybe you can try to share your screen to see that.
Yes, 1 second. Okay, here I think now I can hear you better.
Okay. Let me just, okay. So,
Do you see my screen now?
yeah, let's see.
1 second, I think I should put it larger. Do you see it larger now?
Yes, now it's full screen.
Perfect.
Hi, Professor Sabadini.
Hello, Duvan, how are you?
Fine. Let me introduce Brian Grajales, who will chair your session and who is the also director of the ICMAM project.
Nice meeting you.
Nice to meet you too, Professor. I think we can start now. If everybody can see me and hear me well, then it is my pleasure to introduce Professor Irene Sabadini. Professor, thank you for accepting our invitation. We're happy to have you here, and we're happy to listen what you are talking about. She's presenting her talk entitled A Panorama on the Mathematics of Super Oscillations. So go ahead. Thank you.
Thank you very much for the introduction, and thank you very much for the invitation to give this lecture today. As the title says, I will give you a panorama, so an overview on the mathematics of super oscillations. Super oscillations are not very well known. Mathematically speaking, they have been intensively studied since, let's say, 15 years, more or less. When we started our collaboration with Yakir Aronov, our means mainly with Fabrizio Colombo, Daniele Struppa, myself, plus Yakir Aronov, and mainly Jeff Tollaksen. Then several other people joined the various projects, and you will see the references later on during my talk. But first of all, what are super oscillations? If you read papers about this topic, you will read that super oscillatic functions are band-limited functions which can oscillate faster than the highest frequency that they contain. They have originated in some works of Yakir Aronov and his co-authors in the context of quantum mechanics. So the concept was born in physics, more specifically in the theory of weak measurements. Then they have been further studied by several other physicists, among which Sir Michael Berry and his co-authors. Here I quote two papers. The first one by Aronov Albert Weidman, published in 1988, although the concept was known even earlier. And then another paper published in 1994 by Michael Berry, whose title reminds what is a superoscillating function. The title is Faster Than Fourier. Now, in that paper, Berry explains that Ingrid Dobechies told him that it is possible, at least in principle, to design a band-limited signal with a bandwidth of, let's say, 1 Hertz that would reproduce the Beethoven Ninth Symphony exactly. Now, in the paper Faster Than Fourier, Michael Berry performed the computations. He required that superoscillations, that I will explain what are, for the duration of the symphony. That means about 4,000 seconds. Note that the highest frequency in the symphony is 20 kilohertz. If you do the computations in order to reproduce the symphony using at most 1 Hertz, then it is possible. Michael Berry shows that it is possible. But the signal would have an energy so large that in practice, this is impossible to realize in practical terms. But theoretically speaking, it is possible. So, of course, this is a provocation, but this is to say that with more modest compressions to reproduce the symphony, not using all the frequencies, but some limited frequencies, is possible. So this is to say that the superoscillations have applications in signal processing, super resolution in optics, antenna theory, and also others. Bad news, I'm not talking about applications of superoscillations. I'm a mathematician, not a physicist or an applied mathematician. So if you are interested in seeing applications of superoscillations, you may read this paper titled Roadmap to Superoscillations, which is basically a collection of several papers, one of which is of the group of people that I mentioned before, Michael Berry and others. And it appeared on Journal of Optics 4 years ago. But now let me go to a concrete example of what I mean by superoscillating function. I should say superoscillating sequence. Now define this sequence of functions. N is a natural number. You take cosine of x over n plus I, the unit of complex numbers, a, which is a real number, sine of x over n, everything to the power n. As you will see in a moment, the interesting case is when a is greater than 1. Why we call this superoscillating? Let me note that this function can be rewritten in this way as a finite linear combination of exponentials whose frequencies, you see them here, are bounded by 1 in modulus. The coefficients here in front are expressed by this expression here. Now you note that, roughly speaking, this expression has an exponential growth. It is like a to the power n, and it has plus or minus in front. So these coefficients are exploding when n is growing, and they oscillate. Plus and minus is the sign in front. If you compute for any x in R, the limit of this sequence, you find that in the limit, you obtain the exponential e to the IAX. The convergence is uniform on the compact subsets of R. And now the explanation why it is called superoscillating. You recall that the frequencies in the finite sum were all bounded by 1 in modulus. However, in the limit, the function has a frequency, let's say A, which in principle can be any real number, even larger than 1, much larger than 1, if you wish. Also note that asymptotically, I mean, this function is asymptotic to the exponential e to the IAX. This is visible from this expression here if you take the Taylor expansion at the first order. And so this asymptotic expansion is valid in a neighborhood of 0. How large you can take the neighborhood, of course, also depends on n. Let me show some plots in which the situation is illustrated. Since the functions are complex, we can plot either the modulus of the functions or, as in this case, the real part. And since it is exploding exponentially, I took the logarithm of the real part. But a similar plot can be obtained if you take the logarithm of the modulus. And you see that near the origin, you have some fast oscillations. Here, I plot the case with a equal 4, n equal 20. You can keep a equal 4, and to choose n equal 100, you see the fast oscillations here. The function oscillates less here. And of course, you can play around by increasing a and n, but you still see the fast oscillations here. Note that these functions, this specific sequence that is prototypical, namely, it is the most typical example of a superoscillating sequence, it has some nice combinatorial properties. In fact, compute its pth derivative and evaluate the derivative at x equals 0. Then you obtain this expression, very easy. If you evaluate this expression for p equals 0, you get this interesting relation satisfied by the coefficients. They sum up, giving 1. Whereas if you multiply the coefficients times this quantity here, and you take this sum, then you get A. So this is a very peculiar sequence. Anyway, when we started the collaboration with Yakir Aronov, he was asking us as mathematicians some questions. Now, the questions can be put, roughly speaking, in this way. Question number 1, study the evolution, for example, under the Schrödinger equation, of our prototypical example of superoscillating function. And the question was, when you evolve this sequence of functions, do you still get a function that is superoscillating? In other words, are superoscillations something which is robust and lasts under evolution in time? A related question, we have the prototypical example, but are there other examples? How large is the class of superoscillating functions? Then, to study the persistence of superoscillations under different potentials, still using the Schrödinger equation, also using other type of evolution equations, and then how to extend the notion of superoscillations to the case of several variables. In this talk, I will try to provide an answer to question A, and I will show you that more or less automatically we get an answer to question B, and it also shows the way to answer question D. So let me start with the evolution under the Schrödinger equation. So basically we consider this Cauchy problem in which this equation has this datum. The datum is our prototypical example of superoscillating function. Here the potential is equal to 0, so basically it is the Schrödinger equation for the free particle. Now we could prove a theorem, I will not give the details, that the time evolution of this function here is given by this expression. We have this expression, and the question is this still superoscillating? Well, to answer this question, we have to compute the limit when n goes to infinity. To do that, we need some manipulations. First of all, let us consider this function, that is the evolution of the functions fn, and we note that this function can be in fact represented in this way. Now, let me be more specific. Fn of x stands for Fn of xa for simplicity. And here you see that we have an infinite order differential operator with non-constant coefficients, which depend in this case of the time in this way. Let me provide the idea of the proof, just the main lines. Take the expression in red, this one. This expression can be written using the series expansion in this way. And then using the series expansion, we consider this coefficient, and we note that this coefficient corresponds to the derivative of order 2m of this exponential here. But now, this is a finite sum, so I can easily take the derivative out of this sum. And now you see, here we have what? We have our original function Fn of x. So, of course, I'm not justifying all the details, but roughly speaking, it is true that the psi n are obtained via this infinite order differential operator applied to Fn. Now, heuristically, the limit of the psi n can be obtained as the limit of this infinite order differential operator, which is repeated here, applied to Fn. If it is possible to exchange the limit with this infinite order differential operator, then we know that the limit of this sequence is f of x, namely the exponential. We know what is this limit. And so if we are able to compute this operator applied to fx, we have the answer to our problem. Of course, to exchange the limit with the operator curly u amounts to find a class of functions on which the operator u acts continuously. And this is a question. Now, at the moment, let me proceed, let's say formally. So I am acting like if I can exchange the limit with the operator. So I am applying the operator curly u to the limit function that is this exponential. But this is easy. These derivatives are those ones. But then let me put these factors together. I end up with this. And this is clearly the expansion of this exponential. So basically, my limit function, if I can do these operations, is the product of these two exponentials, the one in blue and the one in red. One exponential is in the variable x, the other in the variable t. So we have an answer to our problem, and we also have an answer to question A. Why? Well, first of all, we see that the formal solution of the above problem gives a function in two variables. And secondly, it opens the way to construct a larger class of super-oscillating functions. Why? We know that the limit, if what we did was fine, mathematically speaking, the limit function is this new exponential. If we set x equals 0, we get that this new super-oscillating function, this new sequence of functions is super-oscillating. Why? Well, look at here. The frequencies are in modulus bounded by 1, and here the frequency is a squared. If a is larger than 1, evidently it is super-oscillating. So we have found another class of super-oscillating functions. And we have also proven that in the limit, the evolution of the prototypical super-oscillating function is still super-oscillating, both in space and time. Note here a feature that may be a coincidence. We will see that it is not. Here I had these special frequencies to the power 2, and here I get a squared. So this 2 goes with this square here. Now, let me go back for a moment to the infinite order differential operator, curly U. Curly U was this operator here, but more in general, we could consider operators, infinite order, of this form, where the coefficients depend not only on the variable t, but also on the variable that corresponds to the variable, the space variable, that here I have denoted by z. Why? Well, the theory of infinite order differential operators works well on spaces of holomorphic functions with growth conditions. So it is necessary to move from the real to the complex setting. So at the moment, I will consider infinite order differential operators of this form. Remember that our operator was this one. Now, what is the class of functions on which these operators act continuously? For this talk, it is enough to define one specific space that here is denoted by A1. I consider a subclass of the space of entire functions. Okay, here it is denoted by the symbol curly H of C. And the subclass is defined in this way. Assume that there exist two positive numbers, A and B, such that f of z is bounded in modulus by A times e to the b times modulus of z. And this is true for all z in C. Let me tell you, one could put a power here, let's say some power, let's say q, and here you get the space AQ. So there are more spaces, not just this one, but this one is enough for today. We have to speak about topology in these spaces because we need the notion of continuity. So we have to describe the topology here. To describe the topology, one needs to define a quantity that is denoted here by this symbol, that is the supremum of modulus of f of z times this exponential. Assume that it is finite. Now, if you take the subspace of A1 of functions for which this supremum is finite, you get a new space, A1b, which is a Banach space. And basically, the topology to say that a sequence is convergent in A1 means that you have a sequence which is convergent inside a specific A1b. Now, it seems a little bit complicated, and in fact, it is complicated. But the good news is that point number one, we have an explicit description of the coefficients of a function which belongs to A1. A function belongs to A1 if and only if there exist two constants, positive, CF and B, such that this inequality holds. Gamma is the gamma function. And also, the continuity can be made explicit as the continuity in a specific space A1b. And the continuity amounts to this condition here. So with these two propositions, we could work inside the space A1. Why I'm saying so? Because, well, the good news are the functions fn of x belong to A1, and our differential operator u is continuous on A1. So what was done purely in a formal manner, heuristically, if you wish, with computations but without justification, in fact can be justified to the last dot inside the space A1. And so we have proven, to summarize, the persistence of superoscillations in time. And we have also obtained as a byproduct a new class of superoscillating functions. Now, we would like to generalize to obtain a larger class of superoscillating functions. Yes, but the natural question is, what do you mean exactly by a superoscillating sequence? So let me first give an intermediate definition, that is the definition of generalized Fourier sequence. It is what? It's simply a sequence of functions of this form. Each function is a finite linear combination of exponentials in which you have that this part of the exponent in red are real valued functions, and here you have some coefficients in front, depending on the natural number n and on another variable a, which is real. Now, take a generalized Fourier sequence, and of course, our prototypical example fit into this definition. Then you say that this generalized Fourier sequence is superoscillating if the frequencies, what I'm calling frequencies, are bounded in modulus by 1. You can also say that they are bounded in modulus by another number k0, but let us be practical and put 1, but you can also use k0 if you prefer. And then there exists a compact subset of R, which will be called the superoscillation set, on which the sequence Fn converges uniformly over the compact subsets to an exponential of the form e to the I g of ax, where g is a continuous real-valued function that in modulus is greater than 1 or greater than the k0 that you have chosen. So, of course, our prototypical example fits into this definition, but this definition, as you may see, is much more general. The classical Fourier expansion is obviously not a super oscillating sequence because this definition is clearly violated. So with this definition at hand, let us now play around. Let us generalize the super oscillating sequence that we got via the evolution using Schrödinger equation, and let us consider this new sequence where here I took the original frequencies to the power p. P is a natural number. We would like to show that also this one is super oscillating. So what to do here? We can consider our initial example, the prototypical example, as initial datum from this modified Schrödinger equation. Note that here I'm taking the p derivative with respect to the space variable. It is possible to show, I will not enter into the details, that the solution of this problem is given by this expression here. Still you get here something to the power p. And it is possible to show that when n tends to infinity, the limit function is the product of two exponentials. And here you have the exponential e to the I t times this expression minus I times a to the power p. As a corollary, when you plug x equal to 0, you get another super oscillating function. This is another one, the one that I was asking myself if it was super oscillating or not. And in fact, with this answer, of course, it depends on the parity of p. If p is even or odd, you have in one case that the super oscillation is kept, and because the frequency is a to the power p. If p is odd, of course, the super oscillation is damped because you get a real exponential. In this case, the infinite order differential operators to be considered are these ones. So the power p is reflected here. It was 2 in the original problem under study. Of course, one can go further because instead of considering this modified Schrödinger equation, where we were considering here the p derivative with respect to space, one can go further and one can consider a polynomial in the derivatives in the space variable, even a series, of course, under suitable conditions in the space derivative. And so one can consider this equation where g is this function here under suitable assumptions, of course. You have our prototypical example of super oscillating function as datum, and you have that the evolution is given by this expression. Note that you may think, okay, this is natural, but be sure that until you do the calculations, it is not guaranteed that this is the form of the solution. And if you take the limit when n goes to infinity, what you get is this expression here. So of course, when you take z equal to 0, you may have, or not, yet another example of super oscillating sequence according to how large is the modulus of G. Now, the material I have presented so far is more or less described in these 3 papers in collaboration with Aronov, Colombo, Struppa, and Tollaksen. But then, are all the super oscillating functions generated by starting with the prototypical one and then evolving? Not really. There is a new method to generate super oscillations. That is this one described here. Assume to assign a set of points, call them hj of n, they depend on the natural number n. All these points are in the segment -1, 1 on the real axis. Take a real number larger in modulus than 1, and ask yourself, what are the coefficients to be put in front of this expression here, this exponential, in such a way that the q derivative of this expression, evaluated at 0, is given by ia to the power q. What does it mean? Basically, this condition expresses the fact that this exponential and these functions, lowercase f of n of x, have the same derivatives at the origin. So they share the same Taylor polynomial of order n. Now, is that possible to determine these coefficients? Yes, we do have existence and uniqueness under the assumption, which is rather easy to fulfill, that if you take I different from j, then hj of n is different from hi of n. Then the coefficients are uniquely determined, and they are given by this product here, which is basically computed via a van der Monde determinant. So we have a new class of super oscillating functions. You see, we have a finite linear combination of exponentials whose frequencies are bounded in modulus by 1. With these specific coefficients in front, they are super oscillating because they give rise to e to the IAX by construction. In this way, we can form other possible super oscillating sequences. In fact, you can take, for example, the hj of n equal to this expression. Note that earlier we considered 1 minus 2 over n times j, everything to the power p. Here we are putting the power p only over n. Now, with this choice of the points in this interval, we have these coefficients in front in order to get a super oscillatory behavior. This method to generate other super oscillating functions is described in this paper. This other paper is a recent follow-up of the previous one. And then there are two preprints going on in collaboration with Colombo, Sabadini, and Iger, where we try to relate the analyticity of the super oscillating sequence and the sampling that we are choosing in the interval -1, 1. And this sampling can be regular or irregular, and there are questions that we describe in these two papers. But now, let me move to the several variables case. Now, by taking the evolution via Schrödinger equation, if you remember, we obtained as limit a product of exponentials in two variables. Each single exponential had a frequency in modulus greater than 1. So we could get basically two sequences of super oscillating functions, one in t and one in x. And as I said at the very beginning, the evolution already in the case of the free particle gave rise to a function in two variables And that contained already the idea on how to proceed to enlarge the class of superoscillatory functions to the case of several variables. But first of all, let us agree to what is a superoscillating sequence in several variables. Mimicking what was done in the case of one variable, we define what is a generalized Fourier sequence in several variables. It is a finite sum of product of exponentials, each of which in one of the d variables, the variables that I consider are x1, x2, xd, and here in front I have some coefficients. The coefficients can be either real or complex. We allow both cases. When we say that such a sequence is superoscillating, well, you may wonder what it means. If all the frequencies are bounded in modulus, let's say by 1, if you prefer by k0, and there exist a compact subsets in which the limit of this function is given by the product of exponentials, each of which in one of the variables, and the frequencies here, G1, G2, GD, are in modulus bigger than 1 or bigger than K0, then you say that your sequence is superoscillating. So basically, this is really the generalization of the notion in one variable to the case of several variables. So one possible example is take our traditional coefficients, the one that we met at the beginning of this lecture, multiplied by the exponential functions, each of which of this form, where here we have some exponents, q1, q2, up to qd, all of them are natural numbers. Now, is this a superoscillating function? A few years ago, we gave a positive answer to this question in a special case, which was already something. Now, assume to consider not d variables, but let's say d plus 1, doesn't change anything. D plus 1 because one variable, let's say, call it x, is special. Why it is special? So each frequency has some power. You see Q1, Q2, QD. Here, the power is, let's say, P. Under the additional hypothesis that P can be written in this form, so there are numbers R1, R2, Rd, that allows you to rewrite P in this form, then it is possible to show that this function is superoscillating. Of course, the question is it possible to have a more general result? The answer is yes. So let me go back a moment. In reality, this result can be proven more in general, so removing this assumption. But in order to clarify how this can be done, I will consider the case of two variables, because the idea is already included in this description, and how to generalize to the case of d variables will be rather clear. The starting point is a superoscillating function in one variable. Assume that it is given and it is this one. Assume that its holomorphic extension, so write instead of x, zeta, which is complex variables, and assume sorry, this is Xi. I always confuse zeta and Xi as Greek letters. Assume that these super oscillating functions is convergent to e to the IA Xi in the space A1, because we need a space where to make some infinite order differential operators act continuously. Now pick two natural numbers, P and Q, and define this new sequence. How is this sequence done? So you keep the coefficients in front, you take the frequencies to the power P in the first variable, to the power Q in the second variable. Then you can prove that in the limit, this function is the product of these two exponentials. We have two variables, and you can see that when A is in modulus larger than 1, well, each of these exponential tells you that the original sequence, this one I mean, is super oscillating in two variables, according to our definition. The proof of the above theorem is based on infinite order differential operators and their continuity. As you can see during this talk, the crucial tool almost everywhere is the theory of infinite order differential operators, and of course their continuity. And in order to do that, the natural space in which to work is a suitable space of holomorphic functions with growth condition. And this can be done also in the case of several variables, starting from just one variable. How? We would like to study a generalized Fourier sequence at the moment in two variables. Denote just as a symbol by dxc, the derivative operator with respect to this complex variable. Now we define this infinite order differential operator, which looks rather complicated, but you will see in the next slides from where it arises. In any case, consider this operator curly U. You see it has variable coefficients. Then it is possible to show that this complicated operator acts continuously from A1 to itself for all x and y in R and P and Q in N. Then we started with this sequence. This sequence has here the product of two exponentials, put the exponents together and rewrite the exponential using Newton, first the power series expansion and then Newton binomial. You get here, and then you note that this part here of the expression, this one, hjn to this power, is in fact, apart from this constant here, nothing but this power of the complex derivative with respect to xi applied to this exponential function, evaluated then in xi equal to 0. So basically, our sequence, this one, is nothing but this differential operator of infinite order applied to the super oscillating function in one variable evaluated x0. And the continuity of the operator curly U implies that we can exchange the limit with the infinite order differential operator. So basically, we are left with the computation of this operator applied to this function here, and then to evaluate at xi equal to 0. And if we do that, if we do these calculations, evaluating xi equal to 0, we end up with this expression that amounts to this power series, that is the power series expansion of this exponential. And so we have our claim. So in the limit, this sequence produces the product of two exponentials, and we have the superoscillatory function in two variables. Now, how to generalize to the case of the variables should be now more or less clear. Of course, all the calculations have to be done appropriately, but you start with your original superoscillating function. You construct a generalized, what I called generalized Fourier sequence in this way. Then, using the tools that I have described, you can show that in the limit when n tends to infinity, you get the product of these exponentials. And when a is in modulus larger than 1, well, you have a superoscillatory behavior. So the theory of superoscillating function in one variable shows how to construct other classes of superoscillating functions, this time in several variables. There might be other ways to construct such sequences, but this is a quite efficient way to produce them. Note that in the case of D variables, we have a much more complicated operator, still infinite order differential operator, and one has to prove that it acts continuously on the space A1, but it is possible to prove that this is true. It is possible to go further and to construct superoscillating sequences in which, instead of taking the powers of the frequencies, here we take simply some holomorphic functions, G1, G2, GD, of these frequencies. And in the limit, you get this expression. And in particular, the expression that you obtain is superoscillating when the functions G, capital G, are in modulus larger than 1. Let me discuss briefly another notion, that is the notion of supershift. So far, we have been playing basically with exponentials, namely, we had some sequences as input, we computed the limit, and we got in the limit exponentials where the frequencies were larger than the input frequencies. But more in general, one can select frequencies of numbers bounded, let's say, by 1 or by a certain K0 positive real number. Take now some entire holomorphic functions. Now you consider functions which are not finite linear combinations of exponentials, but they are finite linear combinations of product of functions, which are these holomorphic functions entire. Then you say that the function, the sequence, has the supershift property if in the limit you get that the functions G1, G2, GD that are multiplied among them are computed far away from x1, x2, xd, because you multiply times a, and a is in general larger than 1. So in the input, you were basically inside minus x1, x1. Here you are far away from x1. And this is a brand new notion that is called supershift. Of course, superoscillations are a particular case of supershift where the entire functions are, in fact, one function, the exponential. Now, let me conclude that the study of superoscillating functions in several variables was done originally here under the additional assumption. Then the notion was extended in these other two papers in collaboration with the colleagues that are listed here. Let me also provide you a general reference if you would like to know more about the mathematics of superoscillations. That is, this memoir appeared in 2017 in collaboration with Aronov, Colombo, Strupp, and Tollefsen. And I thank you for your attention. Thank you very much.
Thank you, Professor Saladini, for your interesting talk. Nice new theory. Now we are open for questions. You can raise your hand if you have any question or comments.
Okay.
The one?
Yes, Professor Saladini, I have a question. I don't know if my question makes sense. Is if in this definition of differential operators, somehow one can consider also a part having the somehow differential operators of negative order, and if this makes sense, let's say in the theory of super oscillations, like pseudo differential operators or something.
Thank you. No, in this theory, the symbol of the operator is always an entire function. So we don't have negative powers.
I see.
These are entire functions, the symbol of these operators. No, at least the theory that we know in which we can work is just this one. Of course, one can consider not just entire functions, because one may wonder, can you reduce to a smaller set? In fact, yes, it is possible to act with some care. I'm not providing details. You can act on disks, but still with positive powers, not negative powers. At least not so far. Maybe this is something that you can work on. Thank you for your question.
Anybody else? No? I have a question, because you, at the end of the talk about supershifts, and I think I want to know if you have developed all the theory of super oscillators in that more general context of supershifts.
Excuse me, but a bus was passing by and there was a noise. Sorry, I tried to. I cannot do that. No, I cannot. Sorry, can you please repeat the last part of your question? I didn't hear it.
Okay, no, that if you have developed some of the theory of super oscillators in the context of supershifts you introduced at the end of your talk.
Yes, to some extent. Of course, there is a C, because you may use a large class of functions, but basically we do have something, because in fact, it is a sort of extrapolation. And for example, if you are interested in a more concrete case, I can recommend you can email me, but there is the case of the harmonic oscillator that is directly connected with the notion of supershift, because the function appearing there is not anymore the exponential, okay? And again, it is possible to push forward the study to some extent, yes.
Thank you. So thank you for your talk. If anybody has no more questions, we can thank again Professor Saladini and continue with our next talk.
Thank you very much. Thank you. Bye.
Bye. Okay, so Professor Virginia Naibo, how are you?
Hello, Duvan. How are you doing?
Thank
Thank you very much for having me. It's a wonderful conference.
Thank you very much. We are happy to have you today.
Thank you.
Especially now today we have, okay, yesterday and today, something about partial differential equations. Later we moved to super oscillations. And now I suppose something more about harmonic analysis. And partial differential equations also.
A very diverse
topic.
Set of topics. Yes, absolutely. Yeah, this is a wonderful idea to have this conference that allows a mathematician from all over the world to meet and listen to talks and talk to each other. So it's a wonderful idea.
Thank you. So maybe then for your talk, maybe can we try it?
To share?
Yes, your presentation.
I'm going. So you should be seeing full screen, correct?
Correct.
Excellent.
Okay. It seems that all is okay. Maybe we can wait a couple of minutes just to be able to more
As you
people
prefer,
to connect.
no problem. Yep.
Thank you. Just a couple of minutes.
So are you in Belgium now or in Colombia?
Now we're in Belgium. Last time when we meet in the seminar of Kansas State University, I was in Colombia.
Yes, I remember you told me, right? Yes.
Yeah.
How's the weather in Belgium now?
Okay, we are moving from the nice summer to the fall weather, so a little bit cold these days.
It's getting, yes, a little bit cooler. The same here, but it's been warm lately in Kansas. So
Kansas.
yes, it's warmer than usual. So yeah, but we are slowly moving to the fall.
Yes, you are from Argentina, right?
That's
remember
correct. Yes,
we talk about that because today we had the talk of Professor Pfefferman, and it was very amazing to see that his second slide was okay. He dedicated his talk to the memory of Alberto Calderon, which was very inspiring, I think, for Latin American people involved in the conference.
Yes.
Okay, maybe let me introduce you. Okay, there are participants. It's my great pleasure to introduce our next speaker. Is Professor Virginia Naibo from Kansas State University from the USA, who will talk about the Newman and Zaremba problems in two-dimensional Lipschitz graph domains. So, Professor Virginia Naibo, please go ahead.
Okay.
Thank you.
Well, hello, everyone. It's a pleasure to be speaking at this ICMAM Latin American Satellite Conferences, Analysis and PDEs. Thank you very much, Duban Cardona and the organizing committee for inviting me and for organizing this wonderful meeting that brings together so many mathematicians from all over the world. And thank you very much to the audience for attending. So I will be speaking about the Neumann and Zaremba problems in two-dimensional Lipschitz graph domains. This is joint work with my collaborators María Jesús Carro from Universidad Complutense de Madrid in Spain, Teresa Luque from the same university, Carmen Ortiz Caraballo from Universidad de Extremadura, also in Spain. And the talk is based on two articles, one in collaboration with María Jesús and Carmen on the Neumann problem in graph Lipschitz domain in the plane, and the other one in collaboration with María Jesús and Teresa on the Zaremba problem in two-dimensional Lipschitz graph domains. So let's start with the classical Neumann problem on a domain omega in Rn. So here we are looking for a harmonic function B in omega. And we would like the normal derivative to equal a given function G on the boundary of omega. So here n is the outward unit normal vector to the boundary of omega. And this equality is interpreted in terms of non-tangential conversions. That is to say, you have a point in the boundary and a cone with vertex at that point, and you approach the point inside the cone. If the domain omega is bounded, then we have to assume that the integral of G over the boundary of omega is 0 in view of the fact that the Laplacian of B is 0 and the divergence theorem. I have made the picture of graph Lipschitz domain here because these are the type of domains that I'm going to work with, but of course this applies to any domain in Rn. Now, as you know, there is extensive literature and work done on the Neumann problem. I'm just going to point out a few references that are connected with the results that I will be presenting. Faves, Chaudhary, and Rivera prove the following result. If omega is a bounded domain in Rn that has C1 boundary in dimension larger than or equal to 3, then the Neumann problem is solvable in LP for P between 1 and infinity. I will define solvability with more details later on, but here think of, you have the solution of the Neumann problem, and you also have estimates, in this case in LP, for the non-tangential maximal operator of the gradient. Jerison and Koenig proved that if omega is a bounded Lipschitz domain in Rn in dimensions larger than or equal to 3, then the Neumann problem is solvable in L2. And this result was extended by Dalberg and Koenig in the following way. They proved that if omega is a bounded Lipschitz domain in dimensions larger than or equal to 3, then the Neumann problem is solvable in LP for P between 1 and 2 plus epsilon. That epsilon is some positive number that depends on omega. And the range of P is sharp in the sense that if P is larger than 2, then there exists some domain for which the problem is not solvable in LP. And analogous results were also proved by Dalberg and Koenig in the case of Lipschitz graph domain in dimension larger than or equal to 3. The corresponding result when n is equal to 2 is due to Faves and Koenig, but it is unpublished. Okay, now let's look at the Zaremba problem. It's also known as the mixed problem for Laplace's equation. So now we have a domain omega, we want a harmonic function B in omega, and now we have two types of data, a Dirichlet data, so we want B to be a Dirichlet type data, we want B to be some function f of d in some open set of the boundary. And then in the complement, we give a Neumann type condition, so the normal derivative should be equal to some given function fn in the complement of D. Again, the equalities are interpreted in the sense of non-tangential conversions. Again, there is a lot of work done regarding the Zaremba problem. I'm going to just point out a few references. The study of the Zaremba problem picked up in the 90s. Koenig motivated the study of the regularity of solutions of the Zaremba problem in Lipschitz domains. He asked the following question: if the data FD, that is the Dirichlet data, has derivative in L2, and Fn, that is the Neumann data, is in L2, what estimates can we obtain for the gradient of the solution? And one of the first answers was given by Brown. It was followed by works by Sikes and Brown. And what they prove is that if omega is a Lipschitz graph creased domain, so by creased we mean a domain that roughly speaking, D and N meet in an angle strictly less than pi, then the Zaremba problem is solvable in LP for P between 1 and 2, including 2. There is also work by Irina Mitrea and Marius Mitrea in bounded Cris domains in AREN with dimensions larger than or equal to 3, and in the setting of Sobolev-Biesov spaces. Lanzani, Brown, and Capogna proved the following result. If omega is a Lipschitz graph domain in R2, with the Lipschitz constant associated to the boundary of omega less than 1, then the Zaremba problem is solvable in LP for p between 1 and 1 plus epsilon. So this is the counterpart to the result by Phelps and Koenig associated to the Neumann problem. And analogous results were also proved for bounded Lipschitz domains, assuming certain conditions on D and N, by Ott and Brown and Taylor and Brown and Ott. And Awala, Irina Mitrea, and Ott also proved well-posedness for the Zaremba problem when omega is a cone with vertex at the origin and the sets N and D correspond to the rays of the cone. So of all these results that I have mentioned, I want to highlight two of them that has to do with our work. Omega is a Lipschitz graph domain in a plane. So we have the result by Phelps and Koenig that says that there is an index P sub n such that the Neumann problem is solvable in LP for P between 1 and P sub n. And there is the counterpart result for the Zaremba problem by Lanzani, Brown, and Capogna. So in our case, what we have done is to find explicit values for Pn and Zn. So for example, for the Neumann problem, we find explicit values for Pn. We prove solvability in LP for P between 1 and Pn. And at the endpoint, in LP and in the Lebesgue space LP sub m, we have solvability in a smaller space, which this is the Lorentz space LPN1. Similar results apply to the Zaremba problem. The proof that we did are use different techniques than the ones in the literature, and they lead to novel and interesting results for the Neumann problem and the Zaremba problem in the upper half plane when the data is in weighted function spaces. We also have applications, for example, when omega is a cone, or more generally, when the boundary of omega is a polygonal curve. Now, before I can give more details about the statement of the results and the tools and techniques that we have used, I need to present some notation and background, so bear with me for a few minutes as I do so. Gamma here is a real-valued Lipschitz function defined in R with constant L, and omega is the Lipschitz graph associated to gamma. Okay. We are going to work with the non-tangential maximal operator M sub alpha. Okay. Alpha is an angle between 0 and the arctange of 1 over L. And here the supremum is taking over the cone gamma sub alpha of C. So this is the cone with vertex at C. C is at the boundary and aperture to alpha. So what does solvability mean? Suppose that X is a Banach space of measurable functions defined on the boundary of omega. So the Neumann problem is solvable in X if there exists a Banach space Y of measurable functions defined on omega and an angle alpha such that for every G in X, there is a solution B of the Neumann problem with datum G, and we have this estimate for the non-tangential maximal operator of the gradient. So we have the data measured in X and the non-tangential maximal operator of the gradient of the solution measured in the space Y. A similar definition applies to the Zaremba problem, and now the estimate for the non-tangential maximal operator of the gradient is in terms of Fn, that's the Neumann data, and the derivative of Fd, where Fd is the Dirichlet data. These are the weighted function spaces that we are going to work with. These are function spaces in R. So W will denote a weight on R that is a non-negative locally integrable function. LP of W will denote the Lebesgue space associated to the measure W of x dx. And we are going to work with the following Lorentz spaces, LP1 of W, LP infinity of W, which are defined in terms of the distribution function associated to the weights W. The relationship between the spaces is as follows. LP1 of W is contained in LP of W, which is contained in LP infinity of W. These are all continuous inclusions. And we are also going to work with these curly L spaces, curly L P1 of W and curly L P infinity of W, which are defined in terms of the Lorentz space LP1 of W and LP infinity of W, respectively. These curly spaces are important because they are going to be the ones used to prove the solvability of the Neumann and Zaremba problems at the endpoints, Pn and Cn. We are going to work with classes of work associated to the Hardy-Little maximal operator. We have the class AP, the well-known Mackenhaupt class AP. And this is a class such that M is bounded on LP of W if and only if W is in AP. And then we are going to work with what I'm going to call the restricted class AP or APR. You can see the analogy between the definitions of the two classes of weight. We have LP here and the Lorentz space LP1 here. We have LP prime here and we have LP prime infinity here. And it turns out that M is bounded from LP1 of W to LP infinity of W if and only if W is in APR. This is what we call restricted weak type. What's the relationship between the classes? Well, AP is strictly contained in APR and APR is strictly contained in AP plus epsilon for any positive epsilon. The set omega is simply connected, so it's conformally equivalent to the upper half plane. We are then going to denote by phi a conformal map from the upper half plane to omega. That map has many properties. I'm going to highlight a few of them. It extends as a homeomorphism from the closure of the upper half plane to the closure of omega. So we can talk about phi of x when x is in R. The derivative of phi in the real line exists almost everywhere and is locally integrable. And a very important tool for us is that the modulus of phi prime is a weight in A2. Now, I'm going to define the indices that are going to play the roles of Pn and Cn. So this piece of phi that I'm going to define now is going to play the role of Pn. It's going to be the endpoint, for the Neumann problem. And it is defined as in terms of the conjugate exponent. So that is 1 over p sub phi plus 1 over p sub phi prime is 1. And so p sub phi prime is defined as the infimum of the values of Q for which modulus of phi prime is in AQ. Remember that the modulus of phi prime is in A2, in the weight A2, and in view of how this class, the properties of these classes, then p sub phi prime is larger than 2, and therefore p sub phi is p sub phi prime is smaller than 2, and therefore p sub phi is larger than 2. Okay. Know that by definition, we have that p is between 1 and p sub phi if and only if modulus of phi prime is in AP prime. And also, if p sub phi is finite, which means that p sub phi prime is not 1, then we have that the modulus of phi prime cannot be in A p sub phi prime. Okay. These are properties that I will remind you of later on as I mentioned them through some sketches of the proof. And now R sub phi is going to play the role of P sub c, the endpoint for the Zaremba problem. The conjugate exponent of R sub phi is defined as the infimum such that modulus of phi prime is in a Q, like for the case of P sub phi prime, but moreover, this expression of P prime is in a Q. And therefore, the relationship between the indices is that R sub phi is less than or equal than P sub phi. Okay, so these are the definitions of P sub phi and R sub phi. P sub phi will play the role of P sub n, the endpoint for the Neumann problem, and R sub phi will play the role of P sub c, the endpoint for the Zaremba problem. Now, I have a questions for the audience. Before I move on, is there any question?
Is there any question for Professor Naibo? It seems that the attendees are happy.
Okay, excellent. Don't hesitate to interrupt me if you have questions. I'm happy to answer questions as I'm speaking. Perfect. So now I'm ready to give you more details about the statement of the results and point to some tools and techniques for the proofs. So here is the solvability of the Neumann problem. We have that the Neumann problem is solvable in LP, that is both X and Y are LP, and when P is between 1 and P sub phi. And at the endpoint P sub phi, we have, assuming it is finite, we have solvability in the Lorentz space LP sub phi 1 with corresponding Y space LP sub phi infinity if the modulus of phi prime is in the restricted class A P sub phi prime. So part A of this result relates to the unpublished work of Faves and Koenig. So we are given an explicit expression for the 2 plus epsilon in terms of P sub phi. Now, remember that solvability, the concept of solvability includes estimates for the non-tangential maximal operator of the gradient. So for P between 1 and P sub phi, we have this estimate in LP for the non-tangential maximal operator of the gradient. And in the case of the endpoint, we have the estimate in terms of LP sub phi 1 and LP sub phi infinity. Now, I want to make a comment between the hypothesis in A and B. In A, the hypothesis is that P is between 1 and P sub phi. But by definition of P sub phi, that's exactly saying that modulus of P prime is in AP prime. Now, also, I said if P sub phi prime is finite, then modulus of phi prime is not in the Mackenhau class AP sub phi prime, but it could be in this larger class. And that's exactly the hypothesis that we are requiring in part B of the theorem. In the case of the Zaremba problem, we are going to assume that D and N are given by the following set. So D is the set of pairs X gamma of X. Remember, gamma is the Lipschitz function that defines the boundary of omega. So we are looking, D is the set of pairs X gamma of X for which X is positive, and N is the set of pairs X gamma of X for which X is negative. And we are also going to assume that phi maps the negative axis to N and the positive axis to D. So under those assumptions, we have solvability in LP, where both X and Y are LP, for P between 1 and R sub phi. And then at the endpoint, if the endpoint is finite, we have solvability in the Lorentz space L R sub phi 1 with corresponding Y space being L R sub phi infinity, under the hypothesis that phi prime is such that this condition is satisfied. So part A now relates to the work by Lanzani, Brown, and Camponia. We have an expression for the 1 plus epsilon. Again, remember that solvability includes the estimate for the non-tangential maximal operator. So we have this estimate in LP for P between 1 and R sub P. And we have this estimate and the endpoint in the Lorentz spaces L R sub P1 and L R sub P infinity. And now what's the relationship between the hypothesis in A and B? Well, the hypothesis in A is that P is between 1 and R sub P, and that's equivalent by definition of R sub P to this condition. And now if you compare with this condition here, the difference is that here we are asking for the larger class, the restricted class AR sub P prime, instead of the Mackenhaupt class AR sub P prime. And well, that's fine, because if we have this if this condition is satisfied, then by the properties of the Mackenhaupt classes, this condition, then this expression of P prime cannot be in R sub P in our AR sub P prime, but it could be in this larger class, which is what we are requiring here. Okay, now I'll move to tell you a little bit about tools and techniques for the proof of these results. So I'm going to start with the tools and techniques for the solvability of the Neumann problem. And we started by studying the Neumann problem in the upper half plane with data in weighted spaces. So we proved the following. The Neumann problem is solvable in LP for P between 1 and infinity if W is in AP. And actually, W being in AP is also a necessary condition for solvability in the case where both X and Y are LP of W. So this statement will be useful for the proof of the solvability in LP for the Neumann problem in the general case when P is between 1 and P sub P. We also prove solvability in LP1 of W with corresponding space being LP infinity of W and W in the restricted class AP. And again, being in the restricted class AP is necessary for solvability for such pair XY. And finally, we prove solvability in the curly L spaces in curly LP1 of W with the corresponding Y space being curly LP infinity of W, and now W has to be in the restricted class AP prime. This item C is the one that is going to allow to prove the endpoint case of the Neumann problem in the general case. And remember that we always have these estimates for the non-tangential maximal operator of the gradient of the solution. I'd like to say a few words about the proof of theorem 5. One can find an explicit solution of the Neumann problem in the upper half plane, which is given here. So that function is harmonic in the upper half plane, and it converges non-tangentially to the normal derivative equals the function g non-tangentially in the sense of non-tangential conversions at the boundary. We proved this pointwise inequality. This pointwise inequality involved the Hartley rule maximal function m, and this H star is the maximal Hilbert transform. And it is very useful to prove the estimate for the non-tangential maximal operator of the gradient. In the case of the first two items, this estimate in the case of the first two items, that equality gives you very easily the estimates in view of the well-known boundedness properties for the Hartley rule maximal operator and the maximal Hilbert transform. But for the curly spaces, we have to work much more. And one of the results used to prove the estimate for the curly L spaces is the following result by Lerner, which says the following: T is a sublinear operator, and then we have associated to T this grand maximal function. And suppose that T and M sub T are of weak type 1,1, that means that these operators are bounded from L1 to L1 infinity. Then under those assumptions, we have this point-wise estimate for the operator. These are averages of, so this is a sum of averages of the function f. And these Q here are cubes that vary in what is known as a sparse family, which I'm not going to define. So our operator T is going to be M sub alpha of the gradient. And once we have these point-wise estimates, a very simple duality argument will give the estimates required in the theorem. So now let's look at the proof of theorem 2, that's the solvability of the Neumann problem in omega. So the proof uses theorem 5, the theorem about the solvability of the Neumann problem in the upper half plane, and ideas that are inspired by tools and techniques from Carlos Koenig work. So here we have the Neumann problem in omega, and we are going to solve a Neumann problem in the plane. So given G, the boundary data to solve the Neumann problem in the plane is going to be the composition of G with phi and then multiplied by modulus of phi prime. And once we have that solution, the solution of the Neumann problem in omega is going to be given by U composed with phi to the -1. Now, note that if G is in LP, then this function here is in LP of this weight here. And this weight is in the Mackenhau class AP if and only if P is between 1 and P sub phi. So here we can apply the results of theorem 2, of theorem 5. If G is in LP1, then this function here is in curly LP1 of modulus of phi prime. And the hypothesis on the modulus of phi prime is that it is in the class A P sub phi prime restricted, and therefore one can apply theorem 5 when P is P sub phi. Now, the estimate for the non-tangential maximal operator follow for corresponding estimate for the non-tangential maximal for the non-tangential maximal operator corresponding to the problem, to the Neumann problem in the upper half plane. But not only that, we need more, and what we used was the theory of Hardy spaces in Lipschitz graph domain that was developed by Koenig. And also we proved some new results about Hardy and weak Hardy spaces in Lipschitz graph domains. So I'd like to show you some examples. Here we have a domain omega whose boundary is a polygonal curve with a finite number of vertices. So here we have the interior angle alpha 1 pi, alpha 2 pi, alpha 3 pi, etc. The alphas vary between 0 and 2. And it turns out that a conformal map from the upper half plane to omega can be given in this form. And you see the alphas show up here in the exponents. These x's, x1, x2, and x3, etc., and a and b are just some numbers. X1 is such that phi of x1 is this point. X2 is such that phi of x2 is this point here, and so forth. And this is what is known as a Schwarz-Christoffel transformation. Now, we have a nice expression for phi, and that allows us to find what modulus of phi prime is. Here it is. And this type of functions was studied by Maria Jesus and Carmen, and they found that P sub phi is given by this expression. That is, P sub phi prime is this maximum here. And also that modulus of phi prime is in the Mackenhau class, in the restricted class A P sub phi prime. Therefore, we can apply our research and conclude that in this case, we have that the Neumann problem is solvable in LP for P between 1 and P sub phi, and that we also have solvability in LP sub phi 1 with corresponding white space being LP sub phi infinity. For example, here is a cone with aperture alpha pi. It doesn't have to be symmetric. If alpha is between 0 and 1, then P sub phi turns out to be infinity. And now we have, therefore, we have solvability of the Neumann problem for P between 1 and infinity. If the alpha is between 1 and 2, then P sub phi is alpha divided by alpha minus 1. And in this domain here, we have that P sub phi 3. Here is another example where the polygonal curve has an infinite countable number of vertices. And a conformal map is given by this expression. And then one can approximate modulus of phi prime with an expression similar to the one studied by Maria Jesus and Carmen, and conclude that P sub phi is 3 in this case. Okay. I'd like to discuss now some tools and techniques for the solvability of the Zaremba problem. So again, we started by studying the Zaremba problem in the upper half plane with data in weighted spaces. In this case, N is considered to be the negative axis and D is considered to be the positive axis. And what we proved was solvability in LP with both X and Y are LP under two sets of assumptions on the weight. In item A, in both situations, we have that W is in AP, and then we have in item A that modulus of X, W of X squared is in AP, and then in item B, we have a different expression in AP. Item B is the one that will allow us to prove the solvability of the Zaremba problem in a general case when P is between 1 and R sub phi. And then item A will allow us to prove solvability in LP when P is larger than R sub phi. But I'll talk about that later. We also have solvability in LP1 of W, with corresponding space Y being LP infinity of W. And the assumption here is that W is in AP and that this expression of W is in the restricted class AP. So you can compare items A and C. The difference is that here we have the class APR and here we have the class AP. And finally, we prove solvability in the curly L P1 of W with corresponding Y space being curly LP infinity of W and the corresponding assumptions on W. And item D is the one that will allow us to prove solvability for the Zaremba problem at the endpoint R sub P. And again, we have the estimates for the non-tangential maximal operators in the corresponding pairs XY. Regarding the proof of theorem 6, what we did was the following. We solved the Neumann problem in the upper half plane with an appropriate data. And that solution of the Neumann problem with appropriate data is going to be the solution of the Zaremba problem with the given data. So what is this appropriate data, boundary data? Well, we define H, the boundary data, to be Fn. That's the Neumann data in the original problem, plus some function P sub D that has the following properties. It is 0 outside D and it satisfied these two conditions. So the first condition has to do with the fact that the derivative of the boundary values of the solution of the Neumann problem coincide with the Hilbert transform of the normal derivative at the boundary. And the second property is so that one can obtain the estimates for the non-tangential maximal operator of the gradient. Well, the proof leads to two possibilities for H1 and H2, and these are used accordingly so that the estimates are satisfied. Now, there are examples that show that the Zaremba problem is not solvable in L2. So both X and Y here are L2. So that means that there are examples that show that for which F sub D prime is in L2, F sub N is in L2, but the non-tangential maximal operator of the gradient is not in L2. Our results lead to the following. For the case of the upper half plane with weight W equal to 0. We have solvability in LP if and only if P is between 1 and infinity and different from 2. And what happens at P equals to 2? Well, we have solvability in L2 with corresponding Y being L2 infinity. So that means that if the data is in L2 then the non-tangential maximal operator of the gradient is in L2 infinity. L2 infinity is a larger space than L2, so it might not be in L2, but it is in L2 infinity. Now, for the general, for the proof of theorem 4, that's the solvability of the Zaremba problem in a general Lipschitz graph domain omega. We use then theorem 6, and we also use our results on the solvability of the Neumann problem in omega. So in this case, the Dirichlet data FD for the upper half plane is the composition of FD with phi in the, and this is the D here is the positive axis. And then Fn, the data for the negative axis that is the same as before, Fn composed with phi and then multiplied by modulus of phi prime. So we solve this Zaremba problem in the plane and then compose with phi to the -1, and this is going to be the solution of the original Zaremba problem. Now, so far, the results for the Zaremba problem consider P less than R sub phi. And remember that R sub phi is less than or equal to P sub phi, the endpoint for the normal problem. So what can we say about solvability for P larger than R sub phi? And under the same assumptions on D and N as before, we prove that the Zaremba problem is solvable in LP if this condition 1 is satisfied. Okay, this is proved using one of the results in the theorem about Zaremba problem in the upper half plane that I mentioned, that it corresponded to item A there. And it turns out that the P's that satisfy the condition 1 form an open interval contained in R sub phi, P sub phi. Okay? So this gives solvability for P larger than R sub phi. I like to present some examples. So here, let's look at the Zaremba problem for cones. We have a cone of aperture alpha pi, and D is going to be the right-hand side ray, and then N is the left-hand side ray here. And so what do our results say about solvability of the Zaremba problem in this type of domain? Well, it depends on the values of alpha and p. So if we have solvability in LP in the following situations, let's say that alpha is between 0 and 1/2. In that case, both R sub phi and P sub phi are infinity, and therefore we have solvability in LP for any p between 1 and infinity. And also the Neumann problem is solvable in LP for p between 1 and infinity. So both problems are solvable in LP for p between 1 and infinity. If alpha is between 1/2 and 1, then R sub phi is 2 alpha divided by 2 alpha minus 1, and P sub phi is infinity. So the Zaremba problem is solvable in LP for every p between 1 and infinity except 2 alpha divided by 2 alpha minus 1, in which case we have solvability in LP1 with corresponding Y space LP infinity. And in item I, the Neumann problem is solvable in LP for every p between 1 and infinity because P sub p is infinity. In item 3, we have alpha between 1 and 2. In this case, R sub phi is 2 alpha divided by 2 alpha minus 1, and P sub phi is alpha divided by alpha minus 1. So we have solvability of the Zaremba problem for every p between 1 and alpha over alpha minus 1, except 2 alpha divided by 2 alpha minus 1, where we have solvability in LP1 with corresponding space LP infinity. And also the Neumann problem is solvable in LP for every p between 1 and alpha divided by alpha minus 1. Now, Awala, Irina Mitrea, and Ott gave a different proof for the solvability of the Zaremba problem in a cone with vertex at the origin. The proof is based on studying sharp invertibility conditions properties for a singular interoperator that is naturally associated to the problem. And their results do the following. In item 3, our results do not say anything about what happens when p is larger than alpha divided by alpha minus 1. This is P sub phi. Their methods do give solvability for p larger than alpha divided by alpha minus 1, except for a few values of p. And also, corollary 9 adds to the results of Aguala and Mitrea and Ott the solvability of the Zaremba problem in some values of p that their methods do not reach. So I would like to finish by making a comparison with the Dirichlet problem. In the Dirichlet problem, we have a harmonic function b in omega, and we want b to be equals to g on the boundary where g is some given data. And the concept of solvability for the Dirichlet problem is analogous to the ones presented for the Zaremba problem and the Neumann problem, except that now the estimate is for the non-tangential maximal operator of the solution. Okay? And there is a result by Carlos Koenig that shows that this problem is solvable in LP for p larger than 2 minus epsilon for some epsilon. Okay? The work by Maria Jesus and Carmen showed that the Dirichlet problem is solvable in LP for p larger than p sub phi prime. So the 2 minus epsilon in this case is p sub phi prime. And then at the end point, we have solvability in LP sub phi prime 1 with the corresponding Y space being LP sub phi prime infinity, if the modulus of phi prime is in the restricted class AP sub phi prime. Thank you very much for your attention.
Thank you very much, Professor Naibo, for this very, very inspiring talk. So we have time for questions. Are there any questions for Professor Naibo? I have many, but I would like the participants to do it, please. Remember that the system of making question is that you can raise your hand, and then we can allow you to make your question just by unmuting yourself. Chat. Okay, so I would like them to start. Maybe, okay, I don't want to make maybe technical questions, just for example, in the slide 7, I took some notes in the slide 7. That you show the result of Lanzani. Right?
Yes.
The result of Lanzani for the Zaremba problem, I think. The Zaremba problem. My question is that you mentioned that the solvability. This is analog. This is the analog of the result of Dalbert and Koenig, right? That you mentioned.
Of Faves and Koenig.
On Faves and Koenig.
Yes.
And in that result, the range of values of P is sharp, right? You mentioned that is.
Well, yes. So so you're referring then maybe to the result by
Okay.
Dalbert and Koenig?
Yes. I crossed
okay.
the.
Yeah. Well, yes. The dimension in any question 2 is due to Faves and Koenig, but that's unpublished. But yes, in the case of Dalbert and Koenig, the result is sharp in the sense that if P is larger than 2, then you can build a domain for which the solution of the Neumann problem in LP is not solvable there.
It's not solvable.
That's the sense where in it for sharpness. Yes.
Okay. Well,
So
and the same happening in the setting of the Zaremba problem. That if P is larger.
No.
Okay.
I don't know. I don't know. It's solvable in LP for P between 1 and some index, but I'm not sure what happens. It's not clear because it's a 1 plus epsilon in the Zaremba.
Okay.
At least for these Lipschitz domains.
Okay, Professor Knight. And maybe at the end, in slide 36, I think, when you compare your result, right, with the result of Awala and Mitrea, is this value P equal to alpha divided by alpha minus 1 somehow critical value, or in this setting?
What do you mean by critical value?
Critical, by the if one can say something about the solvability of Zaremba when P is equal to alpha over alpha minus 1?
Well, well, in that value, no. We don't know what happens at that value. That is the piece of P corresponding to the cones. Yes, we don't know.
Okay.
No, we don't know what happens. Yes, we have strictly less and solvability for P strictly less and strictly larger, but not for the particular value alpha divided by alpha minus 1.
Okay, thank you very much. Maybe, are there any questions for Professor Virginia Naibo? Okay.
Franco wants to see the slide of the bibliography.
Yes. Anyone in particular you are looking at?
Yeah, we're seeing now. Okay, thank you, Professor.
Is that someone asked for the slides of the bibliography, so the slides of references? Thank you, Brian.
There is more. That's why I'm asking if there is a particular reference that they want to look at.
Okay, Professor Naibo, you've seen that people were very happy with your talk. Thank you very much for accepting our invitation. Yours was the last talk today. So maybe I would like to invite maybe to all the people that is in the chat, maybe to open your videos, maybe to know which people is behind of the screen. Okay. So just let me share some words in this final part of this session of the conference. So Derol, thank you for your participation today. We had a very nice participation of Latin American researchers. The talks of Professor Pfefferman, Sekov, Sabadini, and Professor Naibo show how much active is the idea of analysis and partial differential equations from classical problems to problems of PDE involving techniques of harmonic analysis, for instance. So I would like to invite you to attend the talks of tomorrow. We are going to start with the talk of Professor Tobias Kolding from MIT, Enrique Fernández Cara from Universidad de Sevilla, Professor Jenny Fragnelli from Universidad Eclesiástica di Bari Aldo Moro, and Professor Joaquin Krieger from EPFL. So also, I would like to say thanks to our colleague, Brian Grajales, who is also organizer of this conference and who is doing a very nice work streaming our activities on YouTube. So thank you very much, Brian. Thank you very much to all the speakers of today and some speakers of tomorrow that are connected today also. So thank you, and then see you tomorrow in the third section of this, third day of this conference. Thank you very much.
Thank you very much, Duban, and thank you very much, the audience.
Thank you.
Bye-bye.